Good morning all. I request the coordinator to please instruct the participants to join. We will be starting at 10 a.m. sharp. All the coordinators, I request you to please drop message in your respective WhatsApp group so that we can start sharp at 10 a.m. Thank you. There is an important announcement for the today's session. The class will get over by 2:30. So from 2:30 to 2:45, we will be having a small break. Sharp at 2:45, we will start with the MCQ and it will end by 3:15. I request you all to please be connected. Last time there were few issues related that we started at 2:30 and we ended just 1 minute before. This time we are giving a grace time of 5 minutes to all the participants. I request you all to please go through the instructions properly. We will start sharp at 2:45 and we will end at 3:15. So I request you all to please make sure that you are connected well and you start the MCQ question on time. Thank you. Good morning, Puneet sir. Good morning, Ritesh sir.
Good morning, Firoza.
Good morning, Firoza. Good morning, everyone.
So can we start with the session, Puneet sir?
We'll wait for 5 minutes so that people join. Right now, only 117 joined.
Sure. And sir, I have given you the right, so you can just see if you are able to present.
I couldn't get you.
Sir, actually, I have given you the presenter, right? So if you can
All right.
just check.
Yeah, sure. Yeah.
Okay. Thank you, sir. And sir, I already made an announcement as well as I will pass the information to all the coordinators that we will start the MCQ at 2:45 p.m. We will end the class by 2:30 and the MCQ will be over by 3:15.
All right.
Thank you, sir.
Okay, we'll start now. Yesterday we had covered, in theory we had covered UVM architecture, and we had covered in labs we had wanted to cover um, some test benches, but there were problems with some of the people not able to install embedded UVM. So I'll go over the process once more. So that people who haven't been able to do it, they're able to do it now. So very quickly, we need to install embedded UVM, and yesterday in the end there was some issue also where the embedded UVM needed a fix. So I've created a new release which is embedded UVM beta 7, and you can download it, install it. After untarring it, you need to have the bin path, which is wherever you installed it, and then the bin directory, it needs to be in path. So the process for doing it is you need to say path equal to the whole path and then followed by $path. This should give you, if you say type LTC2, it should give you LTC. It should pick, the shell should be able to pick LTC. In addition to that, some people were facing problems with some of the libraries not getting loaded. So what we need to do is we need to set LT library path. So this one variable we will be setting, and we'll be setting to the same place, but instead of bin, we need to set it to lib. So once we have done this much, embedded UVM should be able to, everybody should be able to use embedded UVM, except for some people who I noticed are using very old versions of CentOS or other distros. For example, CentOS, if you're using CentOS 8, you should be okay. But if you are using CentOS 7, any version of CentOS 7, it may be recently released, but CentOS 7 will have old and actually quite old version of C libraries, and therefore it wouldn't be able to link stuff properly. So once we have done this much, we need to look at some of the ready-made code, and I'll go to workshop directory. So I'll delete everything for now so that I can tell you how to do this stuff from scratch. So we will also delete AVST, and then we will say git clone. Git clone, then we have to give https github.com, and then there UVM, and inside that avst adder.git. So if you do this much, it will clone the adder into whichever directory you are presently in. So it will clone it there, and similarly we will clone avmm sh3.git, so it will clone that as well. Okay, now a few more things. Some people may be facing problems with GCC not being there or Git not being there, and so basically the process is, if you are using Ubuntu, then you need to say sudo apt update first, and after you have updated, it will ask you password, so just give it password, and once it has updated, then you need to install Icarus Verilog, GTK Wave, and along with that, Git, as well as Build Essential. So Build Essential will install GCC and related build tools for you. So basically the command for doing that is apt install Git, and then you need GTK Wave, and you need iVerilog, and you need Build Essential. Okay, and if you want to, then you can also install Emacs so that you have Emacs for editing files. Okay, if you do this much, it for me everything is there, so it just says everything is in the latest version. But if some of them is not there for you, it will install that. Okay, so having done that, you can go to AVST header, and we will go through this example. But before that, I just wanted to recap some of the important stuff that we went through yesterday. So what I'll do is I'll share my, okay, so seems I need to get out of this. I'm sharing. So just give me a second. I think I'm sharing only the, I need to share the whole screen, so I'll do that. All right. Okay. So now I need to get down to this place and I need to go here. So these are the slides we'll be covering today, but I want to quickly go through some of the slides that we had yesterday. All right, so here we go. Okay, I hope it's visible to everybody. So I'll quickly go through, not this one, this is old. This is older, so I want presentation slides. Okay. Um, yeah. So a quick recap of what we handled yesterday. Okay. So I want to basically go through the last part. Yeah, this part. So see, this is an example we covered yesterday. So we basically, I'm going through the various aspects of a UVM test bench. So we start with how we conceptualize the test bench. So we'll start with a very simple test bench, and then we'll build over it and see why a UVM test bench architecture is the way it is. So the point being, if you have a very simple DUT, and in this case, we are going to start with a DUT which is more like software. So it's very flexible, it's taking input, and the input is flexible in the sense that we are able to take arrays just like we take in software. Okay, so actually, as we develop this example, I'll be taking a software function and I'll be testing it, and then we will see how the test has to be different for hardware, and I'll quickly cover that because we covered this yesterday. So in terms of software, you have something like a function named sum, and it is having it's getting an input in terms of an array, and the result is the sum of the elements of the array. And then we have a test wherein we invoke sum for an array, and then we find out whether the result is matching what it should or not. And this typical case is, it's called unit testing. And this is basically directed unit testing, wherein we are giving a known input and we are getting a known output. So it's a directed test case in that sense. And the output is called golden reference output because we know what it should be depending on the specification, and the input, given the input, it has to match that particular output. Okay, now even for software, this kind of test case is very simple because we are actually not covering a lot of test cases and we are just covering one test case. So for example, does this software work when the number of inputs is more than 100? Does it work if the output is beyond 8 bits? So like over here we see it can be 32-bit, but does it work in those cases? So all that we need to check. So what we'll do is, instead of a directed test case, we will recommend that the software should be tested with randomized test cases, randomized inputs. So given that we should have a random number generator at the input, and then we should, because it's now no longer a directed test case, we need to have some sort of a checker out here, and the checker finds out whether, given the inputs, whether the output that it's getting from the DUT is correct or not. Now this checker has the same functionality as the DUT itself, and so therefore it's recommended that the person who coded the DUT shouldn't code the checker, because otherwise if he has misunderstood the specifications, or if he is prone to some particular kind of coding style and therefore some particular kind of coding bug, those bugs shouldn't be in the checker as well. So another person writes the checker, and the checker ideally should be coded in another language, because the language that we use for DUT, in some way it dictates our coding style, and a particular coding style is prone to similar kind of bugs. So if we get a similar kind of bug in the DUT as well as in the checker, that bug will be masking the DUT bug. Okay, so now we try to so far as software is concerned, so we think this is good enough test bench for the software. Now we see how things will be different if we want to do it for hardware. All right, so first of all, hardware has a static nature, meaning that by given a hardware design, you will always find it has a specific number of input pins. It can't be flexible. For example, for some streaming bus, or for some memory mapped bus, it will have a specific number of pins for the data. Okay. Now, if in this case, we'll be assuming a streaming bus, and we'll be assuming that the DUT has 8-bit data, which can come in at a time. And therefore, if we want to give it a sequence of data, like we wanted to give an array of data at the input, so that has to be broken into transactions. Okay, so this is where we define this term transaction as something which DUT can take atomically in one cycle. Okay, so you can't break this cycle further. It may be more than one clock cycles, but for data to go in, for example, in streaming bus, you will have a clock edge, and along with that, you will have a valid signal coming in, and the DUT has to be ready for receiving the input. So the DUT also has to exert a signal called ready. So when valid and ready are both asserted, so ready is getting asserted by the DUT, and valid is getting asserted by whosoever is giving input. So when both are asserted and the clock edge is positive, that's the time a transaction happens. So it may take more than one clock cycle. So the transaction will be wherein the DUT gets 1 byte of data, and since we want to give more than 1 byte of data, so there'll be a sequence of transactions happening, and the sequence can be called a frame, and the sequence defines, probably like in UVM architecture or in UVM terminology, it will be a UVM sequence, and the transaction will be called UVM sequence item. Okay, now the transaction will have, every transaction will have two views. So one view is the software view of the transaction, and the other view is the hardware view of the transaction. So the hardware view of the transactions is how the transaction is played on the bus and the various signal values. So it has a temporal nature because the signals will have a reference to time, how they are changing, and the software view of the transaction will not have a reference to time. So it will just be data value. Along with that, maybe the values of some control signals, but mostly just the data value in case of streaming bus. In case it is a memory mapped bus, then the software view will be data value. Along with that, the address specification, and maybe if the bus is more sophisticated, then some sort of masking of the data, because for example, if you are having a 64-bit bus and you are transferring only 32-bit on that bus, then the masking will tell you, or the strobe signal will tell you which bytes are active. Okay, so that will be the software view of the transaction, and there will be a hardware view wherein which can be mapped to waveforms, for example, and wherein we will be able to see how the signals are changing for that transaction to get into the DUT, or in case of the monitor side, the opposite will happen. The hardware view or the signals will change first, and then there'll be some monitor which will take a look at those signals and create a software view, which will be a transaction again. In certain cases, the software view of the transaction will also have timing information. For example, if you want to find out how much latency the DUT is having for for a for some input to go in and the respective output to come out, so you will have a timestamp on all the inputs, and we'll see in the next slide how it will be done. So as the input gets in, so instead of there'll be a monitor which will monitor the input getting in, and that monitor will put a timestamp as it creates the software view of the transaction. Okay, and then the monitor on the output side will also put a timestamp into the transaction. So now this hardware handshaking I already explained. The process of converting a software transaction into a hardware transaction is called the bus functional model. And on the other side, on the output side, there'll be a hardware transaction which will be getting converted to software transaction. So that functionality is also called BFM. To enable reuse, we need to create a snooper and monitor on the DUT input as well, because not all the time there will be somebody, so not all the times the DUT will have open input wherein we can put the stimulus. In case of a more complicated system level test bench, there could be another design, or there could be some other actor which is driving the inputs of the DUT. So meaning thereby this stimulus generation has to be kept independent of the monitoring of the inputs and outputs, because the stimulus generation may not be required in all the use cases. In certain cases, there could be some other actor which could be deciding your inputs to the DUT. For example, in case of emulation, where you need to have very fast inputs to the DUT, so you may decide that you will be using some sort of hardware stimulus generator, and that will be giving the input to the DUT. So your stimulus generation will not be required in those cases. Okay. Now, DUT is usually concurrent. It is having that. So, there, in case of multiple DUTs and therefore multiple test benches, test bench components, I should say multiple VIPs who will be monitoring or generating stimulus for the respective DUTs. So there'll be a very complex test bench, and this kind of test bench will require a mechanism to find out when to end the simulation, and that mechanism in UVM is called UVM objection. So we covered that yesterday. I don't want to go into the details, but because otherwise we won't be able to cover anything today. And similarly, for complicated test benches, because there'll be multiple that you will be generating, you will be creating or building a test bench. So all that happens through something called phases. And in UVM, you have build phase, you have connect phase for setting up a test bench, and then you have run phase for running the simulation. And at the end of the simulation, you will have tearing down of the test bench, which is done through extract, check, and report phases. All right, so we'll end here. And now I'd like to go back to our practical lab session, wherein we will look at some waveforms, we will go through some code, and then we will also go through the more complicated code that we were covering yesterday, that is the SHA3. And there are some remaining slides from yesterday that we'll cover, which are basically for understanding the more complicated DUT and its test bench. So, but before that, we will just go through the ABST header. So, in case things are working for you on your computer, so you can just go through this example along with me. So for compiling the test bench, we just need to say make, and this will invoke iVeryDoc for compiling the DUT, and it will also invoke our compiler, the decompiler for compiling the test bench. Okay, now that the test bench compilation is done and the design also has been compiled, we can just say make run. Okay, so the run was very quick because this DUT is kind of so you can get an idea, like for SHA3 also we are having a similar test bench which is generating a lot of numbers to send into the randomized numbers to send into the input, but most of the time actually is going into simulation of the DUT which is happening in Verilog. So though for compilation, DUT took a lot of time because the whole UVM needed to be compiled, but at runtime, at runtime the test bench is much faster, and the DUT simulation is the one which is taking more time. All right. So a few things here. First of all, it would have generated a VCD file. So we'll take a look at how the VCD file is generated and stuff like that. Just 1 minute. Yeah, so I maximized my screen and then I want to look at Emacs, and in Emacs we'll go through some components of the test bench. All right, so the test bench itself is this. So even if you are coding in system Verilog, there'll always be a test bench and a DUT, and then there'll be a top level wrapper, and that wrapper will be encapsulating both your test bench as well as DUT. So this is that file, and it will be similar in system Verilog. So this is where you'll have a top. So in many cases you just want to call it top, or you may give it a name, and this is where the test bench will get connected to the DUT. In system Verilog, it will be done through virtual interface. So you'll be creating that interface, the actual interface here, and you'll be connecting every signal of the DUT to the interface. And then in system Verilog, you will take that interface to the test bench in form of virtual interface. In embedded UVM, this is slightly different, and it's closer to how things get done in emulation. Okay, so this is the place where you will be connecting the DUT to the test bench. And what you do actually in embedded UVM is you create a BFM. So for creating BFM, you will create all the signals, and so all the signals are read here. See, there are some wires which are corresponding to the outputs from the DUT. For rest of it, you have wires. All right. So for rest of it, you have reds. Okay, so you can control the values of the reds while the DUT will be driving something on the wires. Okay, and then you connect all these signals to the DUT. Now this is somewhere I'll also want to suggest that with Emacs you can do some automation here. Okay, so that kind of automation is, you can always say auto inst in Emacs. Okay, so for example, if you were not having all this over here, you will need, so let me go through this example. It will take me 5 minutes, but this kind of automation is very good in Emacs, and I would like to explain this. So just over here, you will need to add some variable. Okay, let me do one thing. I'm getting digressed, so I'll explain this kind of automation later. First, let me go through the example. So you have all the inputs, and since you want to control the inputs, you declare them as reds, and the outputs from the DUT will be coming in form of wires, so you have them as wires because the DUT will be driving this, so they can't be reds. And then you create a BFM over here. Okay, in system Verilog, this BFM will be part of the driver, but in embedded UVM, this BFM will be part of the top level. In case of emulation, typically in case you are going for emulation as in Veloce, etc., the big emulation platforms, Palladium, Veloce, or Zebu, this part of the test bench is synthesizable, and the BFM actually is synthesizable. So, and then the particular platform will have a way to connect to the test bench, and that way will be via um, DPI interface. So it will be getting transactions from the test bench via DPI. So all I'm trying to say is this is very close to how you will be doing stuff uh, on an emulation platform. Okay, so here we are getting transactions from the test bench via VPI, Verilog Peripheral Interface. All right, so we are getting a transaction here. We are playing it on the DUT. So this is the BFM because, as I said, BFM has a temporal functionality. So given the clock, it will be looking for clock edges, and it will be looking for the control signals, and that's how it will drive data on the DUT. Okay, and then in the end, we want to tell the test bench that this particular transaction has been consumed by the DUT. Okay, so we tell the test bench that my transaction is done. And here you are getting a transaction from the test bench. Here you are telling it I'm done. Okay, so let me go through this DUT, this BFM very quickly. What we are using here is Avalon ST bus. Avalon ST bus is very simple. There are two control signals. The control signals are valid in and ready. Okay, so first we look at ready, and only if ready is 1, that means the DUT is ready, we are going to drive the transaction. Now valid in will, because I am getting a transaction from the test bench, that means valid in is 1, because the transaction is there, that means the test bench is having a valid transaction. So therefore I just wait for ready. A valid part is coming from the transaction in a sense. So in that sense, that if the test bench wasn't able to give me a transaction, in that case valid wouldn't have been active. But since the transaction is coming from the test bench, that means the test bench is able to give me a transaction, and therefore valid is active. Okay, so that's how we go. So we have the ready signal from the DUT. We look for that it should be active, it should be asserted, and the reset should be deasserted, and that's when we will get a transaction from the test bench. And the transaction, as I said, may not have all the control signals. In this case, we just have, because it's streaming bus and it's very simple, we just get data from the test bench, and we also have an AND signal, and this AND signal will tell you that the sequence is over. So like in case of software DUT, we had an array going in. This AND signal will specify that this is the end of the array. This is the last byte in the sequence. Okay, so the DUT also needs that information. So we will first give data to DUT, and then we will give AND signal to the DUT along with data. So actually it's like this. If AND is 0, then we will give AND in as 0, and we will give data. If AND is T AND is 1, in that case we will give AND in as 1, and we will push in the data, and valid will be 1 in both the cases. So there's so we are doing it on basis of what the value of T AND is, which we are getting from the test bench. It will get more clear to you people once you take a look at the waveforms. So let me pull in the waveform so that I can relate the BFM with the waveforms. One basic difference between physical training, where you are training people face to face, and this kind of online training is I'm not able to see people, and therefore I'm not able to get whether you are understanding stuff or not, and whether I should explain more thoroughly and therefore take more time, or I should go faster. So that kind of judgment I'm not able to make. So to compensate that, what we can do is for each of these examples, we can create a topic on the forum. I'll create those topics, and then if somebody has questions or somebody wants to understand more thoroughly, then people can ask whatever they don't understand there, and then I'll respond, or somebody else from the community will respond. Okay, so for now, so we can on that topic we can also, if we are not able to run the test case, so we can also discuss what problems you are getting in the setup. So I'm dumping all the waveforms here. So there are quite a few signals. There is data in, there is data out, and in and out, ready in, ready out, reset, and clock will be there. And then this is T data, and T end is what I'm getting from the test bench. And then there is also valid in and valid out. As usual, the initial portion of the waveforms is all X. It's unknown because the reset hasn't been activated yet. So, but we zoom out and look at the whole waveforms. So then we see that we have valid waveforms. We'll start from the beginning. So this is how. So first we take a look at the sequence level. And so typically the sequence is ending here. So you can see and end. So this is the input sequence. So all this data is going in. And then you can see and out, and between and in and out, you will see data out getting some values. Okay, so then you can also see data out is also having a lot of values throughout, but those values are not valid because valid out is not active. So valid out is active only for this much, and that's when I'm getting the sum of the data which is coming in. So sum of the data values in the whole sequence I'm able to generate from the DUT, and I'm able to put that on the output signal data out. Okay, so that is the sequence view of the the sequence level transaction. You can say the whole all the transactions in the sequence getting finished. And so now we zoom in to look at one particular transaction. So clock is important in the sense that um, only at the positive edge of the clock DUT will be doing stuff. In most of the DUTs, there will be DUTs which will be active at negative edge of the clock as well. But in our case, it's the POS edge. And our test bench will be giving in data which will get latched at the POS edge. So, and along with that, valid in has to be active. Okay, so we see clock edges where valid in is not active. And we see ready in, which is driven by the DUT. So ready in, though it looks like an input signal, but it's actually driven by the DUT. So ready in goes with valid in. Valid in is driven by the test bench. Ready in is, so to say, the DUT is saying whether it's ready or not. And since the DUT is taking input, so that's why it's called ready in. So it's an output signal from the DUT. So DUT is telling you whether the DUT is ready for taking the input or not. Therefore, the name is ready in, but the signal direction is out. And ready in goes with valid in. When both of them are active simultaneously, so we'll put them together. So we'll move this waveform to closer to valid in. Okay. Now, fortunately for us, the DUT is always active. So this is the instance at this clock edge, one transaction is getting finished. Okay, so the value which is going in is 5C. And then at the next clock edge, we see the next value going in, which is 5.7. So then you can also relate the output which is coming from the DUT to what is happening here, but that will be, that relation will not always hold, because that output is only 7-bit, and as soon as a few inputs go in, our sum will be overflowing, so it won't be 8-bit. So you can see B3, which is sum of 5C and 5.7, but valid out is not asserted. That means it's the DUT is saying this is not the data you want to read. Okay, it makes some sense that it's the value is B3, but the DUT is saying don't rely on that. It may be some absurd value. All right. So that's how a transaction on Avalon streaming bus, that's how it happens. The only thing about and in is sequence level. So and in will get activated here, somewhere here. Yeah. So this one. Okay. So when and in is asserted along with valid in, that means it's the last byte of data I'm giving in. This data in, which is 5C. And then since the transaction is over, the whole sequence has been given in, the DUT processes the output, the sum, and it starts giving it on the output. So now we are interested in data out. Okay, so here, for example, in the beginning, you see data out is kind of blank. It's not changing because, but the valid signal is high. So the data out is not changing because the first 2 bytes, which happen to be the most significant bytes, they are 0. And only the last 2 bytes have got some values. We gave an input which was kind of maybe 100 values, and those 100 values were not good enough for the DUT to have some value in the uppermost 2 bytes. So only the lowermost 2 bytes have some value here. And then when the DUT is outputting the last byte, just as we had uh, in the test bench, that the last byte should have AND signal getting asserted. So the DUT is asserting AND out. So that tells the test bench that this is the last byte of the data. So both for input and output, we are following Avalon streaming interface specifications. Though for the output, since there'll always be 4 bytes of data coming out, we could have taken out the AND out signal, because the test bench could have counted that, okay, yeah, I need 4 bytes coming from the DUT. It could have counted that, but since a protocol needs to be respected, so we look at AND out, and we then accumulate all that data and make a transaction in the software for the checker inside the test bench. Okay, now having gone through all this, you will be able to relate this stuff with the BFM. So that's what we'll do now. Okay, so we will take the first transaction, which is happening here, and we'll relate it with the BFM. All right. So in the beginning, the BFM is getting data from the test bench, and it's getting the AND signal. Since it's the first byte of data and we have a long sequence of data, AND signal is not asserted, but that's not necessary. Sometimes you may have only 1 byte of data coming in. In that case, AND signal will be asserted. But in our case, it's not asserted. So this is what gets followed. The data is put into the input of the design, input of the DUT. By the way, for the people who are very new to all this particular file is Verilog based. So we are doing stuff in Verilog. So the syntax is Verilog. And here, what we are doing is, this is called non-blocking assignment. So similarly, there's something called blocking assignment, which is happening here, but this is non-blocking assignment. Okay, so we are giving the data to DN using non-blocking assignment, and we are also putting AND signal on we are putting a value 0 over here because T AND is 0, and then we are asserting valid in. The valid in signal is not part of the software transaction, it's part of the BFM only. So in many BFMs, you will see this kind of stuff where some of the control signals are in the BFM, but not in the, because they are kind of understood in the transaction, so they won't be part of the transaction. So had I kept valid in as one of the elements of the transaction, the value of valid in would always be 1, because whenever there is data, valid needs to be asserted. Similarly, when T AND is getting, so, but we wanted to relate it with GTK wave, and also see the BFM is having a temporal nature. So this is happening after the negative clock. I'm delaying delaying the signals by putting the values on signals by 5 units of time. My unit of time is specified here. So the unit of time is nanoseconds, and this is the precision. So, but if we specify time anywhere without any unit getting specified, the default unit will be taken in case this is, in this case, this is nanoseconds. So, and now see, clock is not part of the BFM in the sense that we are not driving clock. So there'll be global signals. So you can compare this kind of stuff with a PCB board, which will be on which various components will be populated. So clock and reset are not driven by the test bench. They are not driven by the DUT. They are basically, you will have a PLL circuit on the PCB, and that PLL circuit will be creating clock. And similarly, there'll be a reset switch on the PCB, and using that reset switch and also the power on reset, the reset signal will be created. So these two signals are global, okay? And these two signals will not be created by the test bench. They'll be, the global signals will be handled at the top level. All right, so we'll see where clock is getting created. Let's see, clock is getting created here. We have a clock period, and the clock period is defined here as 20 since there is no time unit. So that means 20 nanoseconds. So every 10 nanoseconds, clock is getting toggled. And then there is a reset. So reset is initially 0. After 100 nanosecond, reset is becoming 1. And when reset is becoming 1, along with that, all the signals that I was supposed to uh, give to the DUT, and that was supposed to be done via the test bench. Since the test bench hasn't become active yet, I'll be initializing those signals. Okay, so I'm initializing those signals to a default value. Only ready out is 1, the rest of the signals are 0. Ready out is 1 because 1 is more like default value for ready out signal. Ready out will be ultimately driven by the test bench, and test bench is kind of always ready. So I'm giving it a default value of 1. I could have given 0, that wouldn't really matter. And then at the end of so after, I think I have given reset for uh, uh, some clock cycles, and this kind of specification will be there in the duty, how many clock cycles the reset should be active for. For very simple designs, it's usually 1 clock cycle only, but for complicated designs, since there'll be multiple clock domains in a complicated design, reset is active for multiple clock cycles. Sometimes they tell you to keep the reset ready for 5 clock cycles, or sometimes it may be as high as 100 clock cycles. Okay, so we keep reset active for that much time, and then we deactivate the reset. As far as the BFM is concerned, it will only be monitoring clock and reset. BFM will not be driving it, and it will drive the rest of the signals. So we already covered how the inputs went in. Then we want to cover how the output, we want to monitor as well, right? So then we cover how to monitor, and uh, that will be, actually that's not done here. That's a different BFM, different part of BFM. Here we'll also be interested in, because after I have given in all the signals. So if you see in the waveforms, so after I give valid values on data, and on the and in here, data in and in, let me take out data out to over here. So I want and in, ready in, and valid in close together, and the data value over there. So after I have put value on, after negate clock, I waited for 5 nanoseconds, and so therefore it's in the middle of negate and posage clock. So that's where I gave in data, and then that's where I made valid activated. So since I'm also having ready in, and it is active, so you can see in my BFM. So this is something to be observed. I looked for ready in to be active. Otherwise, I wouldn't have given the data in. So this is one way of doing it. The other way of doing it is I give in data and then keep waiting for ready to get activated. I give in data and valid and keep waiting for ready in to get activated. Okay, so but this is how I have coded for now. So I wait for ready in and then I give in data, and then in the end, because my data has been latched because ready in was active, therefore I give 0 to end in, I give 0 to valid in. Okay, this end in was really not necessary, a valid in was necessary, because now I don't want the DUT to read my data value again. Okay, and finally I'm telling the DUT, telling the test bench that this particular transaction is over. Now, this is the part of the BFM, which is for the stimulus generation. There is another part of BFM, which is for monitoring the input bus as well as the output bus. Okay, so we have a response snooper and we have a request snooper. Request is at the input and response is at the output. Again, we wait for some time in the beginning because the reset wouldn't be deactivated by then, and we could have waited for the reset to get deactivated. So instead of 200, we could have put at the rate negage reset, something like that. Okay. Now, but this is how I have coded for now. So I wait for 200 nanosecond. After that, I start observing the bus. So at every posage clock cycle, because that's what the AVST streaming standard says, all the transactions happen on posage of clock. Again, at the posage, right at the posage, I don't want to observe. I want to observe somewhat later because the DUT may take a little bit of time to make the output available on the bus. So I wait for a little bit and then I look at a valid in. Actually, this particular one is not DUT related. This is test bench related. Again, the test bench may have taken some time, which is not necessarily true. But again, this is where I observe. So at after the posage clock, I wait for a little bit, and then that's where I observe whether valid is active or not. In case valid is active, data in and in these values are transferred to the test bench. Actually, for the request side snooper, this shouldn't be there. So we should actually observe right at the clock edge. And actually, in some cases, it will be preferable to observe before the clock edge itself because we want to make sure that the test bench is making the signals available uh, before clock happens. But this will also work. So, I mean, it really is not so material. And on the output, since the DUT may take some time to activate the test bench, so we wait at the posage clock and then we wait for a couple of nanoseconds and we then see whether valid out is asserted. If it is asserted, then we will take the value of the AND out and of the data out signals and we'll give it to the test bench. Again, there are various ways. It again depends on your implementation. You could have, for example, have this snooper work at the negage clock instead of posage. So this is basically this will in case you are conversant with the system verilog interfaces and the clocking block. So that's how you will do it. In case you for monitoring, you are keeping clocking block to be negage active. So you should put negage here. And in case you are keeping it posage active with some delays, you should put posage with some delays over here. This is the portion where you decide whether you want to dump file or not. In case you don't want to dump a waveform file, so you basically comment this out, okay, like this. Okay, but for our case, we wanted the waveforms, so we keep the waveforms. Then there is a timeout over here. Okay, yesterday I discussed something called objection mechanism, but there could be cases where your test bench gets hung. You know, test bench is also a software, and the test bench may, for example, be waiting for some output from the DOT, and that output never comes. Or there is some problem with the monitor and that output is never observed. In that case, the objection mechanism will fail because the objection mechanism is waiting for that monitor to have sufficient number of output transactions, and that hasn't happened. So for that kind of stuff, we always put a hard value for the simulation to be ended. Okay, so we keep a very high value. This is, for example, um, a million nanoseconds. That will be 1 millisecond. The simulation is actually not ending here. So if you look at the simulation is ending something like 200 microseconds, because there are a lot of sequences and transactions happening. Therefore, 200 200 microseconds, but this was much beyond that. This was 1 millisecond. Okay, so obviously the timeout hasn't happened. In case timeout happens, that means that mostly means your test case has failed because there is some error with the DUT or with the test bench itself. So this is where we are creating the clock. This is where we are having kind of watchdog that after this much time, you always end the simulation. This is where you are putting some stimulus for the reset. Mind it, all this portion is not part of the test bench. Then we have snoopers. This is the BFM part of the snooper in embedded UVM. You do the BFM part in Verilog and then create a transaction and send to the actual monitors. And in case you are driving a transaction, you take it from the driver and put it on the BFM. So having explained all this and having explained the waveforms, I would like to take questions for 5 to 10 minutes so that we can move to more complicated stuff, which is the test bench itself in this case, and then we move to the more complicated test bench, which is the SHA3 test bench. Okay, so if you have any questions, ask now. I'll keep sharing. No, I can't keep sharing the screen because I can't see the questions in that case. So I'll stop sharing, and now I'll look at the questions. So if there are questions, please ask now. There are 14 questions already. So I'll try to answer as many as I can. There's something related to what's the purpose of Build Essential file. Build Essential is a package in Debian and Ubuntu distros, and Build Essential is a, so to say, virtual package. So it's kind of, they have a library of software packages and they call it a virtual package. And it will give you GCC, it will give you the WinUtils, it will give you GDB, which is the debugger. So all these will get installed. So in the sense that all the software development related compiler and utilities will become available to you. How to identify a bug easily? So this is a good question, but needs a very detailed answer. So I'll be brief because we don't have time for detailed answers right now. So firstly, you should try to have very because it's not always good to go for waveforms, and if you are observing waveforms, then you are doing manual stuff. The idea is you should avoid manual stuff, because manual stuff will be, first of all, not very productive. You are spending hours doing something which could be useful elsewhere. So first thing should be, you should focus on having good monitors and good scoreboard. So in case you put a lot of intelligence there, then you will be able to identify bugs automatically, and your test bench will be telling you wherever the errors occur. Okay, so that's about the about identifying the bugs, and that's what UVM kind of methodology will help you doing. But after identifying, you will have to debug, and there also a couple of things become important. One of the things which is important is assertions. So whether they are design specific assertions or the protocol specific assertions, which should be written for your interfaces. And by the way, if you, for example, if you are going to follow embedded UVM and there are no assertions available, then all that can always be done in monitors. Okay, so assertions are, I would say, something called syntactic sugar, and there's always a way of coding the same assertion using an always or an initial block in Verilog, and so that's what needs to be done. So if you want to have good debug capabilities, you should have good number of um, assertions or equivalent always and initial blocks for checking whether your protocol, the interface protocol, in our case, for example, it's the Avalon streaming bus, whether it's getting followed well or not. And then in the monitors, you should have extra functionality. So you should be, in case there is a bug, you should be able to automatically find what kind of bug it is. And then the amount of manual debug should be reduced as far as possible. My laptop is not supporting the given softwares. It's licensed version of Windows. I've updated, but it's interrupted, showing it will update. It will be updated automatically. In mobile, you will not be able to install anything, because mobile will be ARM based, and therefore nothing will get supported. But yeah, I mean, if the laptop is not able to do, probably it's because of internet connection or some hardware problem. So we can't do anything right away. Then, so there are some questions. What is specification of our DUT? Without knowing it, how can we understand what we need to write a test bench? Okay, I have taken this small DUT. I haven't done any specifications here. The point was, it was very simple DUT. For the SHA3 protocol, we will have a specification, and there you will be able to follow it more thoroughly. For for the example we are handling right now, the functionality is as simple as you have Avalon Streaming Bus, and you can download the standard for Avalon Streaming Bus by looking for it on the web. Try downloading it from Intel website, because the other versions may be outdated. So get the latest version, and you will get an Avalon bus standard. Inside that, there'll be a section on Avalon Streaming Bus. So that is part of part of the specification. Except for the protocols of the interface, the specification usually deals with the functionality of the design. In our case, the functionality is, it will take one frame of Avalon streaming data, and it will basically add all that and create an output which will be 4 byte wide, and it will put that output on the output streaming bus with MSB first. Okay, and when you are taking the data input, there is no little endian or big endian in our case, because one byte is coming at a time. When we are giving it out, so we are giving MSB first, that will be big endian. All right. And sir, please explain the switch case, please. Okay, so I'll explain the switch case. Okay, in the code, can you explain argument of case statement? I'll do that. In UVM, we drive DUT signal in UVM driver class, but here we are driving in the top module. So what is the need of AVST driver in in adder AVST file? Okay, that's a good question. There is a need because we are doing two stuff over there. First, in AVST driver, we are pulling a transaction from the sequencer. Then we are normally not doing anything. We could do something for the coverage. Okay, so in this case, we are not, we are having a very simple test bench and we are not dealing with coverage yet. So in our test bench, we are then pushing it to the Verilog BFM, and when we do that, we do it via asynchronous FIFO, which is a special concept in embedded UVM. It helps us with multi-core enabled test benches. Okay, so that's the functionality of the driver, that it is pushing into an asynchronous FIFO so that the test bench can run parallelly with the DUT simulation. Okay, there is a lot of other functionality which I can give you detail about, but wait for a moment. Okay, I'll do it with the code there. Software transaction coming at DB top. Can you explain the connection and communication of the D with the test bench? That's what I'll do when I explain why the driver is there, first of all. So mind it, this is slightly different from System Verilog. But all the functionality is there in System Verilog. You will be doing that functionality in the driver along with a virtual interface instantiation of the interface, but then it will be the same functionality. Now, what's happening at the junction, I'll explain in a bit of time because I'll do it with reference to software. Can you show the command for UVM and SHAT? I don't know what it means. We invoke EUVM compilation via makefile, and then we run the simulation wherein the simulation gets run using basically the simulation is running in Icarus Verilog, and Icarus Verilog invokes embedded UVM because it links it in via the shared object file, and then it invokes it. Okay, so I'll tell you where it happens. Diff between wire and reg. So that is mostly a Verilog question. Wire is something which doesn't have a storage capability, so it needs to be continuously driven. And reg is something which will have a value. So it's like a memory element, and only when it's assigned a different value, it will change. Wire needs to be continuously driven. So I can't go into too much detail here because that will be at least a 15 minutes topic. So you need to refer to some good Verilog book. I can give you reference to good books. So, but you need to refer to a book. Then there is a question about try next item. What does it do? Let me say something over here. See, when you are learning something, for example, if you're learning car driving, then when you press a clutch, then you can operate a gear. Okay, so that's all you need to know about clutch. If you start going into how a clutch works after that, then that's the next abstraction level, which needs to be known by the car mechanic, but not by you. So you can't know everything. If you are, for example, an astronaut, and simultaneously you want to be a rocket scientist also, so you will be mixing up domains. So though I'll tell you a little bit about how this works, but that's something you want to know if you want to actually work in EDA. Okay, for now it is more like uh, at user level you want to know. So you just know that you are taking a transaction from the from the test bench, and that's it. So I'll explain it a little bit, but not in too many details. So if you want to figure it out in more details, so talk to me offline. Is wire always output? No, I mean it's output from one module and it's going out into another module. So it's always output from a module, but it could be input of another module. Sir, in the BFM, we saw some predefined functions like getting next item. So I'll talk more about that, how that happens. Sir, how I get to know my test bench has problem? Please respond. Okay, so if you want to know whether your test bench has problems, see, there'll always be, so one part of the test bench is the UVM part. For example, the connect, you connect various components of the test bench via those FIFO buffers that you use for connections, FIFO import export kind of TLM ports as well. I'll talk about those later in a separate session. So that's one part where you are using UVM infrastructure. So a lot of help will come from the UVM itself. For example, if you have some fundamental error in connecting your test bench components, UVM will tell you. Except for that, you will have functionality. For example, in the scoreboard, you will, if you were having a DUT which calculates CRC of an input stream, then there'll be functionality for calculating the CRC. So you'll code that as reference model inside your test bench as well. So that's where embedded UVM also has support from D language. So there's something called unit test. So you can put some directed test case for that particular functionality inside the test bench itself, and thereby you can make sure that your test bench always works, because you can compile the test bench with minus unit test as a flag. So all the unit tests will be run when you execute the test bench, and say your CRC has some problem after that, so it will be flagged and the unit test will fail. Okay, so that's how you test the test benches. In normal system Verilog based test benches, you have to look for a package called SV unit. So then you'll have to learn that. It's not as simple as it is in embedded UVM, because embedded UVM has first class language based support instead of a package based support. If I would like to write a complete test bench for AXI or AHP, okay, I'll help you with that. Actually, we'll be doing for AVMM shortly, and we will also be doing some AXI based or AHP based test benches later. Sir, can you please make a file of all the commands? I'll try to do that after today's session. I wanted to do that yesterday, but then a lot of people were facing problems installing embedded UVM, and I was awake till late night helping them. In System Verilog, we use mailboxes. In embedded UVM, mailbox is a part of which section? Actually, in System Verilog, you use mailboxes only if you are writing a bare metal test bench. That means you are not using UVM. If you are writing a test bench in bare System Verilog, then you use mailboxes. If you are using embedded UVM, then you don't use mailboxes. You instead use TLM components, which have the functionality of mailboxes in a different way. Okay, so we'll cover that later, but we won't be using mailboxes. In embedded UVM, we have implementation of mailbox, but again, we will be using UVM. Sir, you told that we have generated the clock and reset, I mean global signals from PLL. Okay, I told on a PCB board it is done via a PLL, but we won't be doing that way in our test bench. We will be generating a clock at the top level. So at the top level, in a way, is your PCB board for validation. So I mean, I'm just putting analogy there. So don't take me literally on this stuff. Okay. So when I say it is generated by the PLL, it's generated by PLL on the board. For our simple test cases, it will be done the way I did it. Besides, the point is when we do it in a simple test bench, then in case we want to model the PLL, we should have some jitter component in the clock. And for very complicated test benches, that jitter component is also added. Okay, so on a PCB, it is done by PLL. On a test bench, actually the top, I shouldn't say it's not the test bench, it's the top. The top is embedding or it's encapsulating design and the test bench, and the top needs to model the clock. It doesn't need to model the clock, the PLL all the time, but in case of very complicated test benches, we'll model the PLL and we'll have the jitter of the PLL modeled in the clock. Okay. Then there is a question about, is system Verilog must for TLM? No, it is not. TLM actually is a concept which got started by System C community. System Verilog borrowed it. And there is something called TLM2, which is also implemented in System Verilog, but the complete implementation is there only in C. Okay, sir, can we proceed our research and verification by UVM with available open source software, or do we need to buy out licensed software? Actually, I would encourage people, if you want to do research, use open source, because research will need out of box ideas which you can't anything which is licensed software will be like a very set thinking. This is the way to do it. This is system Verilog. In system Verilog, this is how you do it. And in open source, actually, when we embedded UVM, we are also, when we install embedded UVM, sorry for that mispronunciation. So when we install embedded UVM, we are also installing decompiler, and we have the flexibility. If we want to, then we have the flexibility for going as low as assembly language if we want to change something. So that may not be important for people doing research and test benches, but what may be important, for example, is multi-core test benches, which you won't get with licensed software. And you can also do a lot of research on constraints. Okay, I'll give you example. In Berkeley and in Stanford, they are doing research on constraints, and they want to do constraints which take feedback from coverage. Got my point? That you have a constraint and you want to keep modifying the constraint dynamically as your coverage figures, as different bins of the coverage get filled. Now that kind of thing cannot be done in system Verilog. It can only be done with open source. And for example, if you talk to me offline, I can give you ideas how that can be done in embedded UVM. But that's the point. If you are using something for research, open source is a much better option. You will not regret it, and you will actually regret if you are using a licensed software. Because one part of research always is that other academicians who are in the different parts of the globe, they want to repeat what you have done with a licensed software about 90% of them will not get access to that software, for example. Okay, so there are actually a lot of questions. I'll want to go faster. So one is, after opening Ubuntu, if you are facing operating system specific thing, then we can take it offline. Can we run the same code in Xilinx Vivado? We can't. Xilinx Vivado Verilog simulations are pretty buggy, and the interface with the software with C or C++ is also very buggy. That's what my experience is. So though they are trying to make a very fast compiler, but right now I won't suggest that you use that for any mainstream work. So I'll prefer doing it with Model Sim or with Icarus Verilog. I'm interested in ASIC verification role. Okay, so that is offline. Switch case, I'll explain. EUVM used for verification. Industry, VLSI industry is not very is not good at adopting open source, but we are trying to push embedded UVM into the open source ecosystem of because now a lot of people are doing open source hardware, and that's where we belong. What is bare metal? Bare metal is when you don't use libraries. For example, bare metal, and as far as an embedded board is concerned, will be when you code in assembly language and you don't have an operating system. So that's where people use this term bare metal. But I used it also for system Verilog. If you are creating a test bench that doesn't use any libraries, so that will be bare metal. So that was my kind of usage in system Verilog. But actually it's used for bare metal programming at board level, where you don't have a operating system and you want to run code without an operating system on an embedded board. You can do bare metal programming in C or in C++ or in assembly language. So what's the main difference between UVM and embedded UVM? Again, it takes a lot of time to handle that kind of question, but mainly embedded UVM is completely open source, no license. You don't need system block. It's natively compiled, compiles to binaries, which can be very fast. It's multi-core enabled, and it can be, we'll be running it on embedded systems where it can do stuff which system Verilog will not be able to do. Okay, so just go through the workshop, you'll get to know all those differences. What's easiest way to find the bug in test bench and fix that quickly? Easiest way is gaining experience. So you can't gain that kind of experience by taking lectures. You need to go through the drill yourself. Like, easiest way to learn how to fight on the front is to join the army in the same way. What's the main difference between system Verilog and Verilog programming? System Verilog is object oriented, and also there are other differences like the constraints, the coverage, and the assertions part. But then this becomes an invalid question because there is no Verilog standard today. IEEE ratifies standards every 5 years. In case they don't ratify a standard for 5 years, that standard becomes defunct. So Verilog standard has become defunct. There is only system Verilog standard, and that system Verilog standard includes Verilog. So now there is only a system Verilog. But if people say Verilog, that means 2005 standard. That means the Verilog that used to be there, which doesn't have test bench constructs, doesn't have constrained random verification constructs or OOP or assertions and coverage. If someone misunderstood the spec and write a test bench, then even the design is bug free, it will show error. Yes, it will. Then how should we know this and correct the test bench? You will file this error, and the error will go to the designer, and the designer will then tell you that his design doesn't have a bug and it's probably your test bench, and then it will come back to you. So when you flag a designer with a bug, you should be reasonably sure that the test bench works. So that requires some amount of discipline where you look at the waveforms, you'll make sure that the protocols are getting followed, and you will look at the functionality of your test bench. Probably you should have a unit test for the functionality, and you will make sure, for example, if it's something as simple as CRC checksum, then you will write a unit test and make sure that your the functionality of the test bench is good enough. And finally, if you run a test case and you get an error, you will yourself see whether the design is actually having the error or not, and then only you will flag it to the designer. So initial debug you should do yourself before flagging it to the designer. Do we have LRM for EUVM? We don't have LRM because EUVM is IEEE UVM standard compliant. So the LRM is the IEEE standard for UVM. By the way, when IEEE created the standard for UVM, they nowhere in the standard you will find any reference to system verilog. So it's a standard which is agnostic of the implementation, and anybody who has an implementation which supports the whole standard will be able to say that that's the standard, that's the LRM. Okay, so the IEEE standard is the, you can say, the LRM for embedded UVM as well. So very quickly, since all this has taken a lot of time, we only have half an hour left with us before the break for lunch. So very quickly, I'll go through the code where some people wanted to understand, a little bit about the driver and how the driver communicates with the test bench. Before that, people wanted to understand switch case. In Verilog, instead of switch case, you just have a case statement. And the case statement will have a condition, not a condition, but basically some expression that will evaluate to some value. And that value will be you'll list that value here. So in case you were coding it in C or in D language or in C++, it would have been a switch statement here along with the expression, and then along with these values, which are the different cases, you would be saying case 0, case default, etc. Okay, so how it works is this expression will be evaluated, and then the evaluated value will be compared against the value you have in the different case statements. This is one statement starting from begin to the end, and this is the other one, which actually is the empty statement. Okay, so if it's default, you don't want to do anything. So I could have actually written, instead of writing it this way, I could have written if this particular expression is equal to 0, then begin. So that would have been equivalent. That would have been equivalent in that case, because default for me is anyway empty. So this could have been equivalent, and I don't need a AND case in that in that scenario. Okay, so but if you are using case, then you could have multiple branches, multiple case statements. I actually like the C syntax, switch and case statements. Here it is case, and then you don't know what to say after that. Case branches is what you can say probably. Okay, so that's how it is. And then some people were asking how this thing communicates with the test bench. With the test bench, first I will give you user level. At user level, what's going to happen is, actually let me open that also in the other window. So in one window, I'll have the BFM, And in the BFM, you have ABST try next item. And in the code, you have in the test bench code, correspondingly, you have the do VPI put and do VPI get. Okay, so this is when you are putting a transaction. So for every transaction class, this is my transaction class, my sequence item class, so to say. Transaction is the base class, so you can call it a transaction also, but it's my sequence item class. I'll have two methods for getting a transaction or for putting a transaction into Verilog. So this is my Verilog communication. It's very simple. Okay. By the way, people who have worked with in system Verilog, they will find it slightly difficult to understand. But this put value function is can be having multiple arguments. So if the transaction were more complicated, if say it had address also, then it's like in C++ or in D, it's called function overloading. This is even beyond overloading. This concept is functions that can take variable number of arguments. Okay, so put values can take a variable number of arguments. You just need to make sure that the arguments match the number of arguments and the type of arguments here. So data is over here is 8-bit and byte and is boolean, so that therefore 1 bit, and that's what is it's over here. Data is 8-bit and is 1 bit. So when it's getting an item from the test bench, it's invoking some functions which are defined in PLI. They automatically get defined. So whereas, for example, my transaction is named ABST item. Okay, so for ABST item, the function which will get created will automatically get named like this. And then actually it doesn't relate to ABST item here, it relates to the driver. So in the driver, I am saying that the VPI function and these two get related. And that's how this function under the hood automatically gets defined. And somewhere it will be calling this function to get the actual values from the transaction. Okay, so that's how the binding happens. I'll give you a little bit peep into the binding, so that you can know what is happening if you are interested. But the idea is not to learn that. If you want to learn that, then you need to talk to me separately, and I have to sit with you for 1 hour to teach you. Okay, so this is where it happens in embedded UVM. In embedded UVM beta 7, and therein you go into imports and you go into UVM, and inside UVM you will have components, and inside component you have a special component for
Excuse me, sir.
yeah.
So just sorry for interrupting in between. Actually, all the participants, they are inquiring whether a screen is shared or not. So I request you to please inform that there is no screen being shared, because like they are all the time dropping us a query in the group.
Okay, I'm sorry about it, because I thought I'm sharing a screen. Okay, so that's a big setback, because I was all the time showing code, and so I'll have to repeat a little bit with the screen sharing. I stopped sharing screen because I was answering questions, and then I started. I thought I'm sharing screen, but I wasn't sharing. So let me share my screen. Yeah. All right. So I'll go over it quickly. All right. So I'll go over the code first that I was showing you. Okay. So Control X for Control F, and here you have this. So this is the function do VPI put. Okay, this function has a correspondence with the next item function. Okay, it's a correspondence, it's a binding, but this gets defined elsewhere under the hood. But somewhere where it gets defined, it will be calling do VPI put, and do VPI put will in turn put these values from the transaction and make it available to try next item. Okay, now obvious question is, what if your transaction had more than 2 elements? So you will just put them here. So for example, if it had an address element, then you will put that here and probably in the get um, one also, the function which is there for getting also. Now, I was saying people who have experience working on system Verilog and on Verilog will find this slightly, you know, so to say out of box or slightly bizarre, because the same function can have any number of arguments. Okay, so this in C++ or in D terminology is called variadic function. So I have defined put values as a variadic function. It can take 0 to any number of arguments. Okay, and correspondingly, this function over here will be taking 0 to any number of arguments, because this is a VPI function, and VPI function is getting defined inside under the hood, and it will take the same signature as the function over here. So when we define this function under the hood in embedded UVM, so it will get the same signature, it will get the same number of arguments, and it will have a correspondence, one-to-one correspondence with the arguments of this function. All that is automatically taken care of. So I mean, in many cases when we are uh, interfacing Verilog with C or C++, this kind of thing is difficult to do yourself. But if it is getting done in the package, then you don't want to bother too much about it. Similarly, if you are getting values from monitors, so this is the BFM which is getting values from monitor. So AVST response put, then there are 2 arguments. So that's how it is happening here. Actually, I added address, so I'll delete that. Okay, so this is the user level. User level, you just need to know this. Now, just because there were queries, so I'll quickly show you how it happens under the hood. So we go into embedded UVM beta 7, and into import and into UVM implementation. There you have components, and inside components we are dealing with VPI driver, and that's where this functionality is. Okay, so that's where all the VPI part is taken care of. Here, I'm invoking some really, you call it meta programming. So I'm invoking some meta programming to know how many arguments are there in that do VPI put function and get function, and correspondingly using VPI utilities, I'm creating the related functions in related system tasks in VPI. Okay, so this is where it happens, and this is where the functions get registered. So somewhere here you will find where the function is getting registered with VPI. This call TF is the function, for example, and this is call TF, another call TF for try next item. So now when this call TF gets registered here, and here when it gets registered, its name is given as VPI next try next item task. So the name of this task somewhere, and its name as converted to a C string. So this is how we create it. Okay, so it's some magic. which is done in embedded UVM. And that's how embedded UVM is seamlessly talking to Verilog, and it seamlessly talks with VHDL as well, though that's not part of this workshop. Okay, but when we talk, so this is the board we'll be using, this board. Okay, so when we use this board, then we will see that we'll have to do some low-level stuff, which is not very complicated, but we will be handling when we write into the FPGA and read from the FPGA, we'll be handling that at low level. So that's the beauty of embedded UVM. You are actually able to do low-level stuff as well as the high-level stuff in one language. And if you are interfacing, for example, System Verilog with an emulation platform, then System Verilog has to run elsewhere. Emulation interface has to run on a different platform, and then there has to be data communication between the two. And then you have to learn two different languages because embedded emulation platform will not understand System Verilog. Okay, so now coming back to the test bench. Okay, what I want to do with you people, I want to go through the whole test bench line by line and tell you how it works. Okay, so that will prepare us for the next test bench, which is going to be more complicated. Now, this one hardly has a functionality. It takes in data, it adds the data and sends it out after adding. Okay, but still there is boilerplate. We call it boilerplate code. So typically when people use UVM for very simple stuff, and they'll use UVM for very simple stuff when they are learning it, then UVM becomes, for 50 line DUT, I have written a 367 line test bench. So it's kind of overwhelming that you have to write big code. But then the beauty of all this is, since it's boilerplate code, most of it will be as if you have a template and you are filling in values into the template. So it's already there. You just get that template and you invoke that template. I'll show you how to do it in Emacs. So I'm going to /temp/test.sv, and then I want to create a UVM template for driver. I'll just say UVM, and then it will ask me what you want, UVM driver. If you are able to see my screen, you'll be able to see it. It's asking me what exactly I want to do. Okay, and I say I want a driver. So it brings me a template for the driver. And then see over here, it's saying UVC name, that is UVS component name. And it's assuming, since you are writing a driver, you want to have a prefix driver there, which is mostly the case. So as I change this grayed out part over here, you will see it gets changed in the rest of the template as well. So for example, you see UVC name here where my cursor is. Okay, and you will see it at other places as well. You'll have to search for it, but this is one place you can see it directly. So when I change it, so I want to make it AVST adder. So you see it's getting changed here as well. All right, so it got changed wherever it needed to be changed. And then you also have where it's asking you basically which particular transaction it is it corresponds to. So there you also fill in, for example, for us, AVST sequence item. So it would have changed that as well wherever those changes were required to be there. Okay, so then it asks you for because it's driver, in System Verilog you need a virtual interface. So now in our case, it will be AVST interface because it's AVST driver. So it is AVST IF. So, and you're done. All right, now this code itself is 49 lines, and you took half a minute doing it. And then the real stuff, not the boilerplate, the meat of the code, you will write yourself. So then you know where to write it, send to DUT and all that stuff. And there is some comment also over here with some kind of guideline that, okay, you need to fill in the BFM here. You need to fill in the reset DUT here. All that can be managed. Okay, so when it is boilerplate code, don't get overwhelmed. Just know that you will be able to automate that part, and you will be able to create that part from templates. So for the time being, I'll kill this file, go back to where we were. Now we'll try to go through this code very quickly. First of all, this is again boilerplate. This is how embedded UVM will get loaded into a simulation. Okay, so this is where you specify your multi-core specifications. For example, how many cores you want, how all that detail you specify. Then you are having elaborate test, and you are instantiating your test bench here. Okay, so this is your test bench, and by the way, I mean, in this case I'm taking the default test bench, so it's not defined here, it's defined in the libraries. So I'll quickly go over the stuff, and so I'll start with the driver because that's closer to the BFM. And before that, we need to understand the sequence item. Our sequence item is simple. We have data, we have in some cases data will also have an end flag because it's the last byte of data in the frame. So we'll have data and end. That's because our AVST streaming bus is very simple. In case you have data which is multi-byte, in that case you would have had another signal over here which would tell you like which bytes of the data, especially on the last entry in the frame, which bytes are. So that's a kind of strobe kind of signal, like which bytes are active and which bytes are not active. Okay. So in AVST, that is also simple. It will just tell you how many bytes are active instead of which bytes are active. So AVST tries to reduce the number of pins. And then we have a constraint. This could be, we have a very simple transaction, therefore the constraint is simple. Here I am trying to constrain the data between 48 and 7A. 7A will be something like 112, 122. So basically I want to take only the ASCII characters. Okay, for some reason, I mean, you may not have any constraints, you may have some constraints. And then you have these two functions which let you interface with Verilog code. Okay. Then you have a sequence. We'll go about the sequence later. We'll first go and have a look at the driver. All right. So this is my driver. Okay. So just don't bother too much about this boilerplate code. Okay. This is how it interfaces with Verilog. You know it interfaces with Verilog. After that, forget it. And then you have analysis port. Okay, this is kind of a broadcast port. You can have any number of this is like a source where I'm sending the data from to various. So I'm broadcasting data, and you can have any number of audience over here. So you can have multiple people who want to listen to this stream. This stream I'm making available only for various purposes like functional coverage, etc. But otherwise, it doesn't need to be there. Okay. Now, this is something which is specific to embedded UVM, UVM build. Okay. So what embedded UVM does is in case you have embedded UVM attribute to any component, then it will automatically create a build phase for you. All right. Now we are trying to reduce boilerplate. So basically in system Verilog, you would have had a build phase, and in that build phase, you would be creating this component, and that's it. And that kind of boilerplate, you probably can't even automate, because through Emacs templates, for example, you cannot find out how many or which components somebody would be instantiating. So it can't be automated, but we want to automate it in embedded UVM. So we just provide this, I would say, flag or attribute. If you put that attribute with any component, it will automatically be built. So we can avoid the build phase altogether. You will always, with every component, you will always have a new function in system Verilog. It's called this function in D. So it will always have this kind of signature. So this is part of the boilerplate. You will have a run phase. In run phase, you are getting a transaction, and then you are putting that transaction into the driver, into the BFM, and then you are writing it into the analysis port in case somebody wants it for coverage or something like that. Okay, I'm saying somebody because we need to understand, when I'm writing a driver, then I'm writing VIP for this particular protocol. In this case, like this protocol is AVST, and there may be people who use it, and when they use it, they'll have facilities available for analysis and all that. So somebody, in that sense, I'm writing this code, somebody else may be using it. So I write into that analysis port for any purpose of analysis, like for coverage, and then I wait for item done. This signal will come from the BFM. And then once I wait for that and I get that signal, then I tell the sequence item port, which connects the driver to sequencer, that this particular transaction has been executed. So driver, in case of embedded UVM, it's going to be mostly boilerplate, because the meat of the driver, which is wherein we want to have the BFM, is part of your Verilog part of the test bench. Okay, so driver is like that all the time in embedded UVM. Then you have a monitor. And as you can see, monitor is having analysis port. And since it's a VPI monitor, there is port only on one side. On the other side, it is reading from the BFM. Okay, and where it reads is, just 1 minute. So you have egress. Egress is your port where you're pushing data, and you write into that, and you wait for sequence to get finalized, and you have a sequence item here. Just give me a second. I am trying to, yeah, this is how it will happen. Automatically, the item will come to you from the BFM, and this function will get called. Write function will get called, and the item will be available. So this is coming from the BFM. And you will keep on adding it to the sequence. Now this is slightly like a D kind of syntax. In system Verilog, would have said sequence dot push item, push back. Okay, so you would have said it this way. In D, it's a simpler sequence, a simpler way of doing it, and that is You just say sequence and then that way. So wherever you see it this way, that means you are pushing back. And then I call a function which is asking whether the sequence is finalized or not. So basically that function is only checking for whether the end of frame has come. If the end of frame has come, then it will write the sequence to the upper level monitor. In our case, it could be a scoreboard or it could be another level of monitor. Probably it is scoreboard in our case. Now this monitor will get connected to the scoreboard, and there'll be two monitors which will get connected to scoreboard. One monitor will come from the request size, the other monitor will come from the response size side. Okay, now I don't have that diagram for this simple test case, but we'll have a diagram for the more complicated test case, that is the SHA3, and you will have a better understanding how the components are connected. So we have a driver, we have a monitor, and then we have a sequencer. Sequencer is always a boilerplate unless you want to do a virtual sequencer or something like that. So it's otherwise always a boilerplate, even in system Verilog. So sequencer will get connected to, now you will see sequencer doesn't have a port or anything. Whenever you see a thing like this, you should know that all that thing is already defined in the base class. So sequencer gets connected to driver, and driver has a default and the sequencer has a default port which is available in the base class, and that will get connected to the driver. And then sequencer will be controlled by the test case. So in our case, the test case is defined later here. So there is a default, there's a directed test case, which is quickfox test, wherein you are giving a particular sequence at the input, and then you are checking whether the scoreboard works with that sequence or not. And there is a test case, which is random test case. Okay, so this random test case, so all the test cases and actually all the components will have a run phase. I already talked about run phase today morning and yesterday, that whenever simulation is running, run phase is the one which is running. So run phase will get invoked. I already talked about objections. So objection is raised because the simulation is on. And then I set a drain time to objection. I'll go about it later in the afternoon, how this objection mechanism works and what's the drain time like. But right now we understand that we will randomize, we will take a sequence one by one, we'll have a sequence item and we'll randomize it inside a sequence. So here we are randomizing the sequence item itself. So let me go about the random sequence. So we have a ABSD sequence. So before going to the test case, actually, I should have told you about the sequence. I told you about sequence item, then there is a sequence also. Okay, so let's go about the sequence first. Sequence always has a something called body. Okay, in system Verilog also it's called body. Here also it's called body. So the body of the sequence is where the functionality of the sequence is. It might have some constraint as well. Okay, so just try to figure this in your mind in a visual manner. Okay. By the way, I mean, if you are good at visualizing, you will be good at programming as well. So in programming, it always helps to visualize stuff. So you have sequence items, you have multiple sequence items, and each of those items corresponds to 1 byte of data, which needs to be driven to the DUT. Then you want to create a sequence. Now this sequence you could create in two ways. Either you could have a data structure, and in that case, it would have been in, if you are looking for a data structure, the closest data structure which comes to our mind is an array. So you could have an array of data and then that could form a sequence. But sequence could, instead of forming it in a way like in the way of data structure, it may be much better to form it in form of a functionality, that a sequence item is one by one getting created and getting sent. So it's a function which is creating a sequence item, and it will create multiple sequence items, and it will keep sending those. Okay, so in UVM, it is usually done this way. The sequence itself will be a function rather than a data structure. If you wanted to have a data structure here, you could do that as well. You could create that as an element, and then in the body you could take one element of the data structure, in that case, in our case, array, and you could keep sending it to the driver. So sequence will actually be related to the sequencer, and sequencer will send it to driver, but it's the sequence which will request the sequencer to send it to driver. Okay, so we create one sequence item at a time, we randomize it, and then we send it to the driver. That's how a sequencer will usually work. Now, in this case, we wanted to randomize the number of elements in that array, or in that sequence, the sequence of sequence items, the number of sequence items that will be going. So we also have a variable which we call sequence size. We randomize it with constraints. We are keeping it from 16 to 64. And there is something to it which I'll talk about later, because we are kind of, it's already into lunchtime. So we'll take a break after going through the other parts of it. But I'll explain this part and some other parts later. But let's for now concentrate on this portion only. Some part of the sequence body will be boilerplate, wait for grant, wherein it is waiting on the sequencer that, okay, because in the driver you saw the code where it said item done, and when it says item done, it sends a signal to the sequencer also that I'm done. So when it's saying I'm done, then that's what the sequence is waiting for, that okay, I'll start the next sequence item only when the previous one is done. Okay, so now it waits for that grant, then it randomizes the sequence item, and then if it's the last sequence item in the sequence, then we need to assert and this is part of the AVST protocol, and otherwise we don't assert it, and then we clone the sequence item and send it. So this is what I'll focus on right now before we go for a break. This is important to understand. Now, first of all, request. What is request? You won't see it anywhere. Here I'm initializing it, but otherwise it's not declared anywhere. So if you see any this kind of variable which is not defined anywhere, you should guess where it is defined. So, and in case of UVM, that guess has to be that it is defined in the base class. So this is the derived class, there is a base class. So request is defined in the base class. Okay, and what will be the type of the request? This will be the type of the request. All right. So what we do is it is defined in the base class because of a special nature of what it should be. This is how it should be. So it's a hint to the developer that there is a request. Okay. Now imagine I'll just do it the other way. So instead of request, I'll make it some other sequence item. So I'll say ABST item. Okay, and then I'll name it differently. So I name it ABST request. All right. Now, instead of making it new over here, I'll make it new inside the body. So I'll say ABST request equal to, so I can copy it from here. Okay, so I could have created it here inside the body, and then I could have randomized it, and then there was no need for cloning. Okay, let me comment this, and I could have just sent it. Okay, sorry. So I could have just sent it. So that was one way of doing, and this way is not recommended. So the way you do is you create a new copy in the constructor itself, like it is done here. You are creating a new copy of request, and then you are cloning it. Cloning it means a copy will be created, and that copy will be sent. So when you are randomizing, the randomize function is getting called on one object itself. You can call it randomized object. So the randomized function is getting called always on the same object. And then a clone of the randomized object is sent to the driver. There is a reason behind it. The reason being, if randomize is called on new objects, then it takes more time. If randomize is called on the same object again and again, then it takes less time. Additionally, there is something related to functionality. If you have learned system Verilog, you would have learned about RAND-C. RAND-C is cyclic RAND, though it is not used in most cases. I mean, I have hardly seen anybody using RAND-C. But RAND-C functionality is that an object or a particular variable, when it is randomized and it's RAND-C type variable, then if say it can get four values, it's a 2-bit variable, then those 4 values will not be repeated. So you randomize it 4 times, it won't repeat. Then in the next cycle, obviously it will repeat, but in one cycle it won't repeat. Now, if you have RAND-C kind of variables and you are randomizing, then you have to call randomize on the same object. If you are calling it on different objects, then RAND-C, the reference to RAND-C will be, RAND-C will hold only if it is called on the same variable. If you are calling RAND-C again and again, but on different variables, then there is no reference, and therefore RAND-C will not hold. So to maintain RAND-C kind of functionalities, randomize has to be called on the same object again and again. And then after you call RAND-C, because if you send it to the driver, then next time you'll have to have another object. So you don't send it to the driver, you create a copy and send the copy to the driver. Okay, so there are 2 reasons behind it. One is functionality, the other is efficiency, the runtime efficiency of the program. So for example, in embedded UVM, for every randomized object, we create a constraint solver when you call randomize. And if you are calling RAND-C on different objects, the constraint solver will be new every time you call randomize. And therefore, it will take more memory. And that constraint solver will also be initializing and initialization, because initially you will have to solve all the constraints. So it will take more time. So that's why whether it's system Verilog or it's embedded UVM, every time you want to create a randomized sequence item, this is the way you do it. You use the request variable, which is defined in the base class. Then you do it in the constructor. You initialize or you create it. And we'll be talking about why we are using create function for creating and not new function. But that will happen only after we learn enough object-oriented programming. And then we randomize it, and then we send it after cloning it. So this is important to understand. And after this, we'll take a break. And when we come back from the break, we'll go through the other stuff. Okay. It's 12:15. We'll break till 12:45, and then we'll talk about object-oriented programming, and we'll also talk about the more complicated test bench. Right.
Thank you,
So
Puneet.
right after break, I'll be devoting 10 minutes to question answers. So in case you have question answers, do come right at 12:45.
Thank you, Puneet sir. There is a small announcement. So yesterday in the second half, the attendance was quite low. I request you, all the participants who are connected, that you need to connect post lunch also. There will be the MCQ whose timing has already been shared. We will start the MCQ at 2:45 and we will complete it by 2:30, 3:15. You can take the drive link, share with you. So all the instructions are given. I request everyone to connect in the second half because we are monitoring the attendance of the first half and the second half.
And
So
there
it
are
is
quite a
quite
few
request of all of you.
questions. There are quite a few questions in the MCQ which are from the second half, by the way.
Wow, thank you, sir. So I request everyone to connect us by 12:45, I think, sir.
Yep.
Puneet, sir.
Yes,
Okay.
12:45.
Thank you, sir. And thank you, participants. Please connect.
All right.
Hello, yeah. Sir, can we start, sir? Like 189 people are connected right now. Puneet, sir?
Let's wait for 4 more minutes. Let's start at 12:50.
Okay, sure. Thank you, sir.
Okay, so we'll take a few questions first.
Sure, sir. So, a small announcement can I do on like there are a few queries. Just a small announcement, sir.
Yeah, sure.
Yeah. All the coordinators are requested to please note that the day 3 and the day 4 folders are right now empty as there are some editing going on in the presentation slides. Once that is done, we will be uploading the same. So I request you all to please inform the same to the participant. And in case of anything they need to refer, there is already in the YouTube channel, the recording of the sessions are already available. They can use those sessions as a reference for the content that have been delivered in day 3 and day 4. So the content is already provided. They can refer to the same and all the other related information will be uploaded in the drive. So this is like I informed it to all the coordinators, because one by one I'm getting all the queries from the participants. So this is a collective announcement. So all of you please note. And the quiz drive is already uploaded. So all the instructions are already given. Okay, thank you, sir. So you may start, sir.
Okay, so there are a couple of questions. I will take take them very quickly. There's actually a lot to cover. So one question is about some people are asking about why we still have snoopers and monitors. I think I already explained. We have like the lowest level snoopers in embedded UVM. They are there because we have the corresponding BFM, and they kind of virtually contain the BFM by way of connecting to it. So all the code which connects to the BFM, that needs to be encapsulated, and that's why we have those lowest level components. And then there was a question on UVM do, and the question asks whether there is something related in something analogous to UVM do in embedded UVM. So there have been papers written about it. All these UVM do kinds of macros, they need to be avoided. Okay, so we can we can take it offline, like why they need to be avoided, but there have been DBCon papers need to written about it. So, but we have something corresponding to every command, but that's actually not the recommended way of doing it. And then, okay, every time somebody asks a question, the whole thing scrolls up. I don't know why. Maybe they want me to answer all the questions. That's why they start showing me the first question. Anyway, do we have factory mechanism in embedded UVM? Yeah, we have factory mechanism. Actually, factories are, in D language, factories are there in the language itself. So we take advantage of those factories, and we have a very sophisticated factory mechanism in embedded UVM, which is as powerful as a SC embedded UVM, actually more powerful. So with that said, I will start. So there is a question of snoopers, which I already attended. And then there is a question, somebody is asking what is meant by boilerplate. So boilerplate code is something you need to write, though it doesn't have functionality, or it may have functionality, but it's very verbose, and it needs to be written the same way every time. Okay, so that's called boilerplate. And so when I was discussing about, for example, the sequencer, I called it boilerplate because there's nothing to understand there. It's just a instantiation, or not even instantiation. It's you derive from the sequencer class, make another class, but don't do anything inside it. So since it must have a function, constructor function, and some related stuff which is there all the time but doesn't have any specific functionality, so you call it boilerplate. All right, so now I'll go through the slides first because there is a lot to cover, and in the if and when we get some time in the end, then we will cover the more advanced test bench example. So this is the slides I want to cover. There's actually, we will be covering till just enough OOP. We'll be covering design patterns tomorrow. So there is actually a lot to cover. So I want to share my screen first. Okay, so hope it's visible to everybody. And then we go about the slides. Okay. So first we go over perils of non-agile design. Difficult to change. Okay, so before I start, say there are two types of software, I would say, development flows. So, or like they apply to verification as well. As I said, verification is software. Even design is software. Now that we design everything in Verilogs, and Verilog is a language, it may be a domain specific language, but it's a language. So now in software domain, there are two kinds of flows. A lot of people, a lot of attendees may have heard about it, but let me go into a little bit detail here. So one flow is where you have waterfall flow. You call it waterfall. You have specification, and unless the specifications are complete, you don't start the design. And then when you are designing, unless the design is complete, you don't start verification. And unless the verification is complete, you don't go for physical design, and so on. Now, this is called waterfall because you go from one step, and just like water will go from up to down, you are going in the flow. The specifications come first, so you complete the specifications, and only when they are complete, you go down. And this kind of flow has issues because, for example, when you are creating a chip, then your specifications will be ready. And if the chip is getting designed from spec, you may take as many as 3 years to finally have a fabricated chip. So in that 3-year period, the market situation may have completely changed, and the specification document that you created 3 years back is completely outdated. So that's the kind of problem with waterfall, and therefore there's no market for the chip once you're done. So instead of that, there's a flow called agile flow, and we discuss what agile flow is, and we will be going through. So it may, kind of the attendees may feel that it's a digression, it's not related to verification, but it's very much related because from philosophy, we want to see how to create test benches, how to program in an object-oriented way, and why it is required. So unless those concepts are clear, so we will not be able to appreciate what object-oriented design is. So let's start with that philosophical background. So first we'll see the problems with non-agile or the waterfall design flow. So when you use waterfall, you have these perils, or these are called smells. Okay, so if you have designed something badly, there is a smell in it. So one problem is rigidity. Difficult to change design even in small ways. So if you are using waterfall, it is okay because once you design something, you may not be required to change it because the specification is not going to change. Okay, so with waterfall, rigid designs used to work. So you still could work with Fortran or other non-object oriented languages, but with agile flow methodology, agile design methodology, you can't have rigid designs. So every small change cascades into subsequent changes in dependent modules. When managers let loose their team on a required change in design, the engineers disappear for a long time because everything is tightly bound. You have global variables, you have functions, and you don't know how many functions will access the same global variables. There's no encapsulation like in a class structure. The global variables are lying in various files, and maybe 50 functions are accessing a single global variable. And when somebody is accessing a global variable, he doesn't know who else is accessing it. And he may make a change in that global variable and doesn't know what the repercussions are. So this kind of things are rigid. Okay, so rigid is where there are too many bindings, and if you want to change something, you don't know what else is getting affected. So first you find out what else is affected, and then because something else is affected, you may have to so that any change in one module kind of cascades or perpetuates into changes into other modules. As a result, managers try to block any request for a change or in the requirement or in the architecture. So that's what it's waterfall design, where the whole architecture, etc., because it's going to be based on the it's going to be based on the specification document, and specification document doesn't change. So in there it may work, but with agile design methodology, it won't work. Okay. So then is fragility. Fragility is similar to rigidity. So rigid is like it doesn't break, but it's very hard, so difficult to change. Fragile is it's again hard, but as you try to change it, it will break. So that's what every change, however small, breaks the design in unexpected ways. A small bug fix may result into a barrage of unrelated bugs, many of them resulting from the fix itself, but getting caught much later. So the customer will report a bug, and the bug will be fixed by one of the engineers, and the fixed package or the fixed software given back to the customer, and the customer then starts facing 10 more bugs. The management and the customers lose their trust in development team as a result. Then is immobility. Immobility basically means that you have a software module or some package which cannot be reused. And as we saw with Moore's law, we need more and more reusable design as well as verification. That's the idea of verification IPs, and that's the very idea of UVM, because UVM, the main advantage of UVM is that it makes things reusable. So inability to reuse the design in other projects or parts of the design in other places in the same project. So that's immobility. The design may have been too tightly integrated with other modules, thus forming a baggage that is too difficult to remove. Okay. For example, I give you an example where instead of black box verification, we were verifying, say, SHA3, and the verification environment looks inside the design, looks into some of the signals inside, and thereby it is a tight binding, because the same verification environment, when somebody else implements SHA3, the interfaces are going to be same, but the internals of the design are going to be different. And when the internals are different, this particular test bench is not going to work because it's expecting a particularly named signal inside the design. So may result from poor encapsulation, not following standard coding practices, or rules that might sound trivial, such as naming conventions. And finally, viscosity. Viscosity is where if you want to make a change, then it's difficult to follow standards. The standards are made in such a way, and these standards would be wrong standards. They are made in a way that if you need to follow these standards, then it will take too much time, and therefore you try to hack things. Okay. And viscosity is more often in methodology rather than in the software. So for example, we use version control system, and like for our workshop, we are using Git along with GitHub. So in case Git is difficult to use, people will tend to copy, people will tend to create changes in a way that will be difficult to go back into the repository. So all these things will be viscous. Viscosity can be in design and in development environment. Viscosity may result from employment of non-standard ways, often resulting in more viscous systems at a later stage. Like we used to have version control systems like CVS, where checking in things used to take a lot of time. So people will avoid checking in stuff for months together. So that kind of systems. A major source of viscosity in chip industry may stem from lack of interest in software tools like version control. I mean, even if the tool is good, if you don't learn it, then it will become viscous. Now, changes in requirement, and as I already discussed, because the development cycle is too long, the point is the specification document will change. So many of the software perils we discussed result from changing requirements. Requirements are often changed in a way not anticipated by the designers. Requirement document is the most volatile document, and we must realize this and plan ahead for possible changes in the requirements. Why it's most volatile? Because there are too many actors there. Requirement document will be made by some technical marketing team, and that team will be interfacing with multiple customers. And as soon as there is a new customer, he'll have his own requirements. And an old customer might come and say, okay, whatever you were doing, there is a chip which is already now available in the market. So in case you want me to buy your new chip, so please add this functionality. Otherwise, I'll go with the other vendor. So that kind of things will happen. And therefore, the requirement document will keep changing. It will also change with 3 years is a big time. Even 1 year is a big time. As you are making or going through the development cycle, there might be a new standard, and you may have to adhere to those new standards which may have come in the meantime. So now this is slightly off place slide. I just added it, but I wanted you people to, understand abstraction and how abstraction in test benches is. So on the right hand side of the slide, I have added Ethernet frame and how Ethernet has only 4 layers, unlike ISO communication layers which have 7 layers. Ethernet has only 4. So as we move up, abstraction increases, and as we move down, abstraction decreases and more details come in. So you have more concrete frames, more information as you go down. As you move up, there is less of information. Like at the application layer, you may not even know if that particular data is going to go to another client and who that client is. I mean, this all is about networking. In verification, you still have layers, and this is how the abstractions go. You have UVM base class library, which is the top abstraction. And then you have top level test bench integration, which comes next, then verification IPs, and then the test cases. Now, somebody may get confused because UVM is a library. And normally when people start, say, working in C or in Fortran kind of language, then a library comes at a lower abstraction. It's something you use at upper layers. So for example, if you are creating some networking software, then the library will implement Ethernet CRC functionality, Ethernet frame structure, and stuff like that. So that's more detail. And when you use that library, then you will be using that Ethernet frame structure, and you will be creating packets, and say you will be doing routing. So routing of those packets, which is a higher level abstraction than the lower level abstraction which came from the library. Now, in case of base class libraries, there is an inversion in terms of abstraction. We'll learn more about it, but this is important to, whatever we are going to learn, it will be very, very object-oriented, domain-specific knowledge. So we need to see how it relates to verification, and that's why I added this slide. So the UVM base class library is the top level abstraction. Then top level test bench integration, where you will be using multiple verification IPs. You'll be integrating those and make the top level test bench work. Or even if you have one verification IP, you will be writing the top level, TB top or some Verilog module like that, where you will be integrating DUT as well as the test bench. So that's the top level integration. So that comes next after the base class library. Then comes the verification IPs, and below that the test cases. So as we move on, we'll see how this whole thing is and how it works. But just just to add there, when you want a verification methodology like the UVM, then you don't even know which domain you are going to work in. For example, if you are making a networking chip, then the verification IPs and the test cases that are going to be related to communication. And if you are working in, say, a processor domain, then those IPs and test cases will be related to compute, like the ALU and the cache controllers and stuff like that. So you don't even know the subdomain of hardware where your methodology is going to be applied. So that's why it's very high abstraction. You want to have generic stuff. Okay, whenever you are doing verification, you need to construct a test bench, and you need to connect various test bench uh, constructs like the driver and the sequencer, and you need phasing mechanism to synchronize between the various components of the test bench, as well as you need a mechanism for terminating the simulation. So these are higher level algorithms. These are not domain specific. And as you start using this library in your verification project, you add the domain specific knowledge. You buy verification IPs, which are going to be related to networking if you are doing a networking chip. And as you integrate those, you will fill in other details. For example, how the reset and clock are generated, which particular IPs and how they get connected together. And finally, the guy who writes test cases, he'll be putting in the final details. For example, he'll be saying exactly how many or what kind of test cases need to be run, and which particular verification IPs will be active in which test case. So as you move from the top to the bottom, abstraction decreases, details increase. But the point is the top level flow, how the whole verification needs to be structured, those need to be in a library, and people who are writing those libraries don't have the finer details. Okay, so this kind of inversion, so to say, wherein a library needs to be at the top and the details need to come later, we will see how it is enabled by object-oriented programming. So first, there's some fundamentals. We go about the fundamentals of agile programming, because agility is what makes object-oriented programming important. Agility is where not only you expect a change, you are ready for a change all the time. So in that way, agility increases reuse, because immobility is one of the factors which is against reuse, which goes against reuse, and immobility is part of the waterfall, not a part of agile programming flow. So agile programming is where you take care of rigidity, viscosity, immobility, and fragility. None of these is welcome, and you welcome change, because you know change is going to happen irrespective of whether you welcome it or not, but you're ready for it. So the manifesto of agile software development, we are uncovering better ways of developing software by doing it and helping others do it. Through this work, we have come to value individuals and interactions over process and tools. Okay, so individuals and interactions, if you map it to what I said, for example, you interact with your customers and you don't bring in processes. You don't say, oh, my specification document is already done, so no change is welcome. You have a working to have a working software. I mean, you basically value a working software more than comprehensive documentation. You value customer collaboration over contract negotiation. You value responding to changes much more than following a plan. That is, while there is value in the items on the right, we value items on the left more. Okay, so understand this, that it's not like we want change to happen, but we know change will happen. And therefore, we value the highlighted portions here, value the uh, items on the left much more than the items on the right, because if we value the items on the left more, then we will be open to changes, we will take changes, and we will be flexible, we will be more reusable in that manner. So now, so having said that, we start with WOOP. As we go into different principles of WOOP, we will relate to agile programming. We'll find out how they make it more visible to, for example, uh, follow the agile principles and not be rigid, viscous, or fragile, or what was the last one? Rigid, fragile, viscous, or immobile. So we don't want any of those four bad smells. So we'll see how object-oriented programming, if we follow the principles of object-oriented programming, then those bad smells will go away. So the point is, I'll be teaching you object-oriented programming from principles rather than telling you what inheritance is, what virtual functions are. I believe all of you must have gone through all that while reading some books, etc. We'll talk about that. We'll talk about that in a little bit, but we want to understand why they are there. You may be using the best object-oriented programming language, but if you don't know the principles of OOP, you will never come to design a good object-oriented program. So just for some basics, there are limitations to a human brain. Okay, and those limitations are, one of those limitations is, if say for example there is a human and he is loaded with multiple activities. So if he's loaded with multiple activities, he will kind of it will be difficult for him to cope up, and he will start failing. So people who researched into all this, they found a magical number 7 plus minus 2. I mean, so there'll be people who will be very brainy like Einstein, and there'll be dumb people like some politicians. So now the dumb ones will be able to cope up with only 5 things. The bright ones may be able to comprehend 9 things at a time. So the average is 7. So numerous experiments have shown that human mind can actively manage about 7 pieces of information. This capacity of human mind is known as working memory. One thing you can relate it with is the processor. And if you don't go with 64-bit processor, you go with 32-bit processors and all, you will see a lot of those actually have 7 registers or around that number. And then you have a RAM. So RAM is like memory, which is long-term memory. And the registers are like the memory which are available right away. So whatever processing is done in a processor is always done on the registers. Similar is human mind. So it can keep some things at the top of the mind and some things in the background. So the capacity, the experiments have shown that only about 7 things can be kept at the top of mind at any given time. Given the limited capacity of the human mind, how can we go about making complex verification environments and other systems? So one way is we create complex but incomprehensible systems that you yourself will not be able to understand when you revisit after 6 months. So see, the machine which is going to actually compile your test bench, or it's going to simulate. So it's not about that. It's about writing code which is reusable, which is manageable, which is not rigid or fragile. So that code has to be understandable by the human being. And there, the recommendation is 7. Therefore, you can have 7 things at a time, but not more. But if that is the limit, how can we make such systems? Because we saw rigidity, we saw fragility. It's about binding, it's about variables which are getting accessed by, say, hundreds of functions. And then those variables, if one of the functions is changing, you don't know what else is using it. Okay, now the idea is to encapsulate, the idea is to make sure that not more than seven people are using it, for example. So if you change a variable, then you know what are the 7 different places where there are going to be repercussions. So this kind of thing can be done via encapsulation. We'll see in a little, but right now we will develop this theory more, and we'll see how the human mind works. So the point is, when we say human mind can take only 7 things at a time, those 7 things may be very simple, or those 7 things may be very complex. So, but the number has to be 7. For example, those 7 things maybe if you open the engine of a car, then those 7 things may be the plug out there, the spark plug, or the piston, or the the pistons go inside a cylinder, so all those cylinders, or the combustion mechanism. So so those 7 things could be those details, or it could be the engine itself. So as soon as you close the engine, you know what 7 things are there inside, but you ignore those. It's just an engine for you. And then you become the user of the engine. So there'll be a car mechanic who is an expert of the engine, and he'll be able to open and work in it. But there'll be another mechanic who just doesn't know what is inside, but he knows how to connect the engine with the other stuff. Okay, so in the previous session in the morning, we were talking about various aspects of embedded UVM, and then there were some questions about how the monitor or the driver interacts with the BFM, and that's where I told you, okay, if you want to understand that, then that's slightly more detailed than what you should understand, because if you start understanding those details, if you focus there, then you are not focusing on the test bench. You will be having more than 7 things, for example, to say. Okay, so if you have more than 7 things, then you will not be able to comprehend. So as an example, I'll give the example of car engine again. So say you have a car where the encapsulation or abstraction is not done properly, and therefore when you change a gear, how that gear gets changed through different levers, and how it changes the transmission mechanism of the car. If all those things are visible to you while driving the car, you will have difficulty in focusing on driving. Okay, so there is a book on how to design things, and when you work through all these things, you will realize all the common things that you interact with in your day-to-day life will have approximately 7 interfaces. If you talk about a car, you have a gear stick, you have the driving wheel, you have indicators, you have the wiper, you have the horn, you have then that dial, how much the speed is, and you have the clutch and the brake. So approximately 7 things. If you have a more complicated system, if somebody makes a car with many more interfaces, then initially people might like it, but then as it goes into the market, people will start avoiding it. because it's too complicated to handle. So this is about working memory. Chunking refers to the strategy of making more efficient use of short-term memory by recording information. So if you have to uh, remember a number which is more than 7 digits, your mind will try to chunk it. Okay, this is code for India. This is the STD code for Gurgaon. And this particular code, this is the local code for my exchange. And then is the rest of the number, which is particular to the guy who I'm interacting with. So this is called chunking. So some things can go into long-term memory. For example, the STD code or the ISD code. So a chunk indicates to long-term memory structure that can be used as a unit of perception and meaning. And then in my working memory, I won't have the 9-1 detail. I'll just have detail of, okay, it is India code. Okay, this is Gurgaon code. So on the top of the memory, it will be only a chunk rather than the all the digits of the number. Okay, so another chunking example. So we have chessboard, and the chessboard has so many combinations and permutations. So the people who are grandmasters, they are probably the people who can comprehend 9 things at a time. But still, the number of permutations on a chessboard are too many. So the way they comprehend is by making groupings. These 3 things, how they are fortifying my king, or how a particular combination of the rook and the queen, how it is going to strategize my game. And even if it's about moves, they will be thinking in terms of chunk of moves. I'll make this move, after that this, after that this. So that makes a combination. Okay, so that's what chunking would be in game of a chess. Now we directly come to chunking in software. So if we were to make a program in C for Ethernet frame, and by the way, Ethernet frame has exactly 7 fields, including the preamble, destination address, source address. The type of the type field will be the one which indicates what kind of Ethernet packet it is. Then you'll have the payload and the data size, and finally the CRC. So you can count, there are 7 things. So just to emphasize on that, there were other standards for networking. If you go back in 1980s and 90s, there were other standards. All those standards faded away and Ethernet won. So one thing which will strike out will be the simplicity of the frame. Many of the other frames had many more complicated fields, and therefore people will not knowingly, but in a very subtle fashion, they'll start avoiding those. Okay, so today 99% of the network traffic is carried over Ethernet. Procedural programming languages such as ANSI provide data grouping structs that enable user to manage complex data structures in a hierarchical manner. So C language will provide you structures, and thereby you will have some sort of chunking. But if we compare it with a board of chess, then the position of various pieces in chess, it's about data chunking. But the chunking at level of how many moves we are going to make and what the moves are, that's the functionality. So that is absent in C. So functions are not associated with structures. Functions are all global. Okay, so programmer coding the higher protocols need to be aware of the structural details of Ethernet frame. He may just use a set of library routines to process the frame as per the lower layer protocols. So here we are just saying, just like a car mechanic will know the internal details of how the car works, but the car driver doesn't need to. Same way, in software, we'll have layering, and this layering will be the guy who is writing the frame structure of Ethernet will be another one, and he will know the structure of the frame. The guy who uses the frame doesn't need to know the structure of the frame. He can just call functions. All right, so that's how the ISO layer structure, or the layer structure I showed a little bit earlier here. So that's how it becomes important. There'll be a team who will work at link layer, and that will be probably the hardware team. Then internet transport and application teams, they'll all be different. So each layer provides a set of services to the other layer, but how those services are implemented, how those details are, will be hidden from the upper layer. Okay. Now, from there, we go to object-based programming, where the functionality also starts getting chunked along with data. Okay, so in a game of chess, the moves are also related to what kind of piece it is. A move which is related to the rook will not apply to the queen, probably. In case it applies, then there'll be some sort of inheritance. But otherwise, the moves are data specific. Okay, so therefore, functionality also has to be encoded along with, encapsulated along with the data. So here is what it becomes in C++, because we have encapsulation at that level. So we will have service layer. Service layer is the public methods, and we'll have implementation details. And the service layer itself, only the method signature will be visible to the end user. How the method is implemented, those are the implementation details, will not be visible to the client of this class, the guy who is creating an object of this class. So those details will not be visible there. So object-based languages, and this is not yet object-oriented, this is only object-based. Object-based languages allow grouping of functions pertaining to a given struct along with the other attributes of the struct. Attributes are the data of the struct. The attributes may actually be hidden from the user. In this case, they are private. So private is indicative of, okay, the user shouldn't touch them. User doesn't have access to the private members. So in that way, hidden. Allowing access of them only through qualified methods. These methods are often termed user interface of the class. Now, go back a little bit. I talked about binding. I talked about global variables in C. So the problem was it's a globally lying data, and everybody has access to it. Everybody can modify it. Everybody can access it. So you don't know how many people are, trying to modify it, how many people are using it. So in that way, if you change data from one function, you don't know, the other functions don't know that this function is which other functions are changing data. So that's what you make data private or hidden, so other people can't have access to it, and you make that access possible only through a sane manner. Only the people who know how to change that data will be allowed to change it. Other people will be kept away from it. So in that way, you create very well-defined layers, and you create a set of team who are the team for this abstraction, and they'll be changing these variables. They'll be handling data here, and the other people will not be having access to this data. So thereby, we are reducing a lot of binding, and that will increase reuse as well. So a class is a contract. So a class is a contract. What's the contract part of the class? The public methods. Actually, there is a criticism of some languages like C++, even D will go in that group of languages, or System Verilog will also be in that group of languages. And that criticism is that though these private members are off access, like I can't modify or access them directly, but they are visible. It's like I'm the driver of a car, though the engine is covered by the bonnet, but the bonnet is transparent. And therefore, when I'm driving the car, I can actually see inside the car, what is there inside the car. So it will make my driving uncomfortable. You, uh, you must have seen, all of you, a kind of wristwatch which has a lot of visibility inside. Like there won't be any dial there. There'll be only those pins moving on top of a lot of gears. So now, though that kind of watches fail to serve the purpose, because if you are looking at time, you will take some more moments to really understand what time it is, because your focus will also go on the gears which are moving. So that's not the right kind of abstraction. Only only the things which are useful to you should be visible to you. So here, some hidden details are visible to me. That's not good. That's how C++ and all these languages are. These functions are not visible because they go into another class and another file. Here I'm only talking about the header file. So the implementation details are slightly off the hook, but visibility wise, there is some criticism. So every class is an interface, meaning thereby the public methods of a class. These are the ones who the client can access. So unless I change the public methods, the client will not be affected. If I change the implementation of some of these methods, then the client is not affected. If I change the signature of the method, then the client will be affected. So the point is, if I'm creating layered software stack as the verification environment is, so a change in the UVM base class library, even if somebody needs to change the implementation of that library, and that change shouldn't be visible to other people. So you have the implementation details shouldn't affect the clients. All right. So so that's where the contract nature of the class comes into picture. That there is some part of the class which is visible to the customer, and this is the contract between the customer and the implementer of the class. Even if he changes the implementation of the class, he shouldn't change the interface. So contract is very similar to, for example, if you are uh, doing a contract, a sale contract, for example, then there'll be terms of sale. There'll be a license in which of the terms, like how a software or hardware or whatever that sale is about. So there'll be a term about its usage. So all that is a contract. So similar contract in software is the public interface of a class. The private and local data members are implementation details. These could be used in an unauthorized manner if not declared private. So if I start exposing private parts of a class to the customer, then it will be like failure to keep the contract. Contract may not be written in a document. A lot of times it is in terms of an API document, but then you have to enforce it in software itself. So for example, I could still write object-oriented programming in C, but I'm not empowered enough because there are no constructs to hide data. So still, if I follow standards, if I follow, for example, some document which defines the API, and then I know, okay, these functions are related to this structure, and this is how to use it. So, or I can, there are ways to have function pointers and make them make a function look like data. So if I use all that, I may still be able to write very beautiful programs, but the language is not supporting me. So object-oriented languages where the support comes from the language itself. So that support is coming in terms of that I am able to hide implementation, and I am able to expose only the useful parts to the customer, to the client. So now comes the 5 principles of object-oriented programming. We start with the first principle, which is the single responsibility principle. Every object should have a single responsibility, and that responsibility should be entirely encapsulated by the class. All its services should be narrowly aligned with that responsibility. Now, why this principle? Because every responsibility is a reason for change. For example, in UVM, you have UVM object, but if you start exploring UVM object inherits from UVM print object. So there is print functionality because every object can be printed. So, but printing is one responsibility which is aligned with the object itself, because object has fields, and those fields need to be for purpose of debug and for purpose of investigation. Those fields might need to be printed in log reports. So therefore, print is an aligned service. Okay, but if I add printer to the object itself, so printer is a different service, but print is an aligned service. I want to print the object, but the printer will be slightly different, because printer is when to print and which file to print. There can be log files, and it could be what information to print and what not to print. So all those finer details which are related to printing, that's encapsulated in another class. If you start mixing the class, there'll be chaos. There'll be tight binding. So if I, for example, instead of having 10 classes in a test bench, so if I don't have monitor and driver separately, if I mix up things, then it's as good as having global variables, because you just have a very big encapsulation which encapsulates everything. So it becomes just as having global variables. Okay, so the single responsibility tries to define how to make out where to have that encapsulation. If a test bench needs to have 10 components, or it needs to have 2 components, or maybe 100 components. So this is how to decide. A class or a module should have one and only one reason to change. So that's the single responsibility principle. The next principle is open close principle. Software entities, classes, modules, functions should be open for extension but closed for modification. That is, such an entity can allow behavior to be modified without altering its source code. So this is important in verification in 2 different ways. So one is the way of the object-oriented programming itself, because we want to make it possible, for example, to have a generic frame of Ethernet. But then if somebody wants to have jumbo frames, now jumbo frame can have thousands of not thousands of kilobytes, thousands of bytes of data. So, but that's a specific category of Ethernet frames. Okay, so if you want to make something more concrete, then you inherit from it, and you have that kind of functionality added there. But otherwise, it will be a generic Ethernet frame. Okay. Similarly, if you look into the banking sector and say you are making a software for a bank, then you will have a bank account, and that bank account will have certain features, so which will be specific to the bank. Now, obviously, every bank account will have the name of the holder. There could be multiple account holders. So it will not have the names of the account holders. It will relate to the bank account, will relate to how many holders are there, and then there will be an account holder, bank account holders class itself. So that will be a different class than the bank account class. But in terms of making it open and closed, so there'll be a current account, there'll be a saving account, there'll be a loan account, there'll be a fixed deposit account, there'll be there are forex accounts. So all those are extensions. Okay, now why not allow modification in the base class? Why allow to create extensions or to create derived classes in system Verilog? In system Verilog or in embedded UVM, you can create derived classes, and that's how you create extensions. But what's the funda behind it? It is like every class is going to have clients. So there'll be softwares like, for example, the audit software will be looking for all the accounts, and then it will call. So every 3 months, the bank is having audit, and lot of audits these days is done by software, and then the software will point out certain accounts either randomly or based on the data that particular account is showing. So the audit software will flag, okay, all these accounts need to be manually audited. Now I'm talking about the software. So the audit software will pass on the responsibility of audit to the class itself. So inside the bank account class, there will be an audit function, and that audit function shouldn't be specific. If I start adding in the base class itself, if I start adding uh, functions for current account in the base class itself, then other kinds of accounts and their clients will start getting affected. Okay, so the idea is to have as less rigidity as possible, and yet you shouldn't be repeating yourself. So there is a principle in programming called "don't repeat yourself." So yet the base class will have the basic functionality, the functionality which is common to all the bank accounts in our example, but whatever is specific to different types of accounts, so those will be implemented in the derived classes. So this is what open close principle is. Now open close principle is the principle which allows us to which basically is implemented through inheritance in object oriented languages, but it's the most important principle if you want to understand how it allows you to create that layering structure which reduces binding. So let's see an example. So you have a crypted frame which inherits from a frame, and a crypted frame has extra functionality whereby a crypted frame, whenever a frame is getting sent, or it is, so byte pack is that abstraction which is used for sending a frame. So before a crypted frame will be packed into a buffer to send to another, to the network or wherever it is going, or if it's going to the um, to another layer, for example. So it will be byte packed, and at the time of byte packing, it will be encrypted. While a normal frame will not have encryption getting invoked while it is getting byte packed. Okay, so that's how the byte pack function itself is virtual, because it is inheriting or overriding the one defined in the base class. Well, but the encryption function, which is specific to the crypted frame, is inside the crypted frame extension, and that's where it is getting defined. So I have given all this in C++, but it is readable code. Okay. Now, uh, inheritance is a relation, because, for example, crypted frame is a frame, and unlike other class methods, a virtual function is bound at runtime instead of compile time. We cannot instantiate objects from virtual classes if they are purely virtual. In C++, classes with pure virtual functions, in D or in embedded UVM, these functions will be marked as abstract functions. In C++, class objects have to be passed by reference, like pointers, if we need to if we wish to change the virtual functions that get invoked. So that's a slight detail of C++. Let's not bother about that. In embedded UVM as well as in system Verilog, classes by default are passed on by as pointers. So virtual functions will always get invoked. Virtual functions are implemented using a table of function pointers. That's some detail you need not bother about right now. So now let's go into an example where I want to explain how this concept of open close principle or the inheritance allows us to create layered architectures, layered software architectures. This code is written in C, just for letting you know that C cannot support this kind of thing. So they have different kinds of. So now this is an example related to the networking domain. You have a lower layer where all the different kinds of modems are, and the modems, the different modems, they actually implement dial and that layer functions which implement log on at the higher level. So one is session layer, the other one is probably transport layer. So the transport layer functions need to be defined by the transport layer, and this log on should be visible, should be defined in the other layer, in the session layer. Okay, so let's see. So don't try to go too much into the details of the functions in C over here. Just try to comprehend the logic or the concept out here. So whenever a new modem is required to be added, the logon method will need updation. Now logon is session layer method, and it will need to be updated because a new modem has been added. So a new modem, for example, could be like there is a modem from Hayes and Courier. There may be a modem from, say, what's that company? Let's take Coilcom. So maybe there is a modem from Coilcom, and that needs to be integrated. So now the logon function, because it's done in C, will have to call in case it is seeing a Coilcom modem. So it will have to call dial Coilcom, right? Because these functions have been made available by different modem companies, and depending on what kind of modem it is, you'll be calling the lower layer functions. Okay, so this is what happens in C. In C++, it will be, you have a public interface. You have a base class, which is modem, and which defines the transport layer functions, dial, send, receive, and hang up. Okay, so these are base class functions. This is the contract of the class. This is the interface of the class. Now, the lower class will be implementing, the transport layer will be implementing this, and the session layer will be using these functions. Okay, so we'll see more about it later, but this is what the principle is, and this is why you are able to segregate layers. And this is exactly what UVM is meant for. In UVM, you will have base class library. Now this is the base class, for example, the modem is the base class. So now this base class library will tell you what functions need to be implemented in the lower layer, that is the transport layer. Okay, similarly, so upper layer is defining what the lower layer should do. So similarly in UVM, the upper layer will give you the base class virtual functions which haven't been defined and which need to be implemented by the lower layer, while at the upper layer itself, that is, in this case, that layer is the session layer. The lower layer functions are grouped together in a higher level algorithm to implement a higher layer function. Okay, so you have upper layer has the base class, and then there is lower layer which takes this base class, inherits from it, and implements the lower layer details like the dial, send, receive, etc. So It will take time to comprehend, but we'll revisit this concept later on as well. So next principle, Liskov substitution principle. Liskov's notion of behavioral subtype defines a notion of substitutability for mutable objects. That is, if S is a subtype of T, then objects of type T in a program may be replaced with objects of type S without altering any of the desirable properties of that program. So it's all about the behavior of objects. Okay, so Liskov substitution principle tells you, so open close principle told you, okay, basically it defined inheritance. Liskov substitution principle tells you when to use inheritance and what should be the base class and what should be the derived class. So though this is technical language, let me tell you simply. So if you have a base class as a bank account and a derived class, for example, could be the savings bank account. So there are properties of a bank account and there are properties of a saving bank account. Okay, so in case you are given a document which defines that these are the properties of a bank account, you should be able to substitute in that document wherever bank account is written. You should be able to substitute bank account with savings bank account, and all those properties should hold. In that case, you should be able to derive from bank account and create saving bank account. Okay, now there are cases, there are very subtle cases where you think that, okay, this should be inheritance. This kind of thing should be inherited from a base class, but that doesn't hold. So let's take that kind of example. Is a square a rectangle? So mathematically, every square is a rectangle. So we will say if there is a rectangle base class, then square should inherit from it because every square is a rectangle. So is it a good idea to derive a square class from the rectangle class? A typical example of example that violates LSP is the square class that derives from rectangle class, assuming getter and setter methods exist for both width and height. Okay, so that's where emphasis comes on the contract of the class or the interface of the class or how the class is perceived by its clients. If it's a rectangle class, then a client may like to change its height, for example, irrespective of its width. But it can't be done for a square. Okay, so if you have used Microsoft Visio or the other graphical softwares, one good software is Inkscape, which is available both in Linux and Windows. So if you have used that kind of software, you will realize if you create a rectangle and you create a group of shapes, it allows you to stretch that whole canvas in one direction. So all the shapes will be stretchable. Now, if that kind of canvas also has squares, so how to stretch that? You stretch a square and it will become a rectangle. So properties of square will not be kept. There need to be some, so to say, assertion on that square that, okay, the width and height will always be equal. So those assertions are called in software, they're called invariants. So that's an invariant of the square class that will not hold if we allow stretching in one direction, but a rectangle must allow stretching in one direction, and that kind of interface for a rectangle cannot be there for a square. So you will not be inherit a rectangle and make a square because you will not have a way to define the virtual function which is there to stretch in a particular dimension. The square class always assumes that width is equal to the height. This is called invariant of the square. If a square object is used in the context where rectangle is expected, unexpected behavior may occur because the dimensions of square cannot be, or rather should not be, modified independently. this problem cannot be easily fixed. If we can modify the setter and setter methods in the square class so that they preserve the square invariant, then these methods will weaken or violate the precondition for the rectangle setter. So the setter function has a specific, or the stretch function, if there were one in the rectangle class, will have a specific expectation of the user, and that expectation will not be met. So you are breaking the contract. Okay, so therefore, a square in software terminology is not a rectangle if rectangle is having a getter or getter method for a setter method for independently for width and height, which usually it will, or maybe stretch kind of methods there in the base class. So whenever we look at classes, we have to have a client specific view, because we have to maintain a contract. We can't let go of that contract. That contract, if we start, the public interface of the class is the contract, and we have to hold that. We can't change that. We have to adhere to the expectations of the customer or the clients of the class. When we think about LSP, also think about the client interface. Does the derived sphere class have the same interface as the base type, which is a rectangle? If it doesn't, you can't have inheritance relation between the two. Is-a versus has-a, two objects are said to be related to each other by has-a relation if it is aggregation. For example, a computer has a screen. A computer has a processor. So the computer, if we were modeling a computer in software, then computer shouldn't derived from the shouldn't be a class which gets derived from processor. It should rather have a component which is processor, or it should have a component which is screen. Okay, so more often it's the has a relation than is a relation. So more often you want to have components in a class than to use inheritance. Okay, so typically because of that 7 plus minus 2 formula, typically almost every class will have at least 4 or 5 components. Okay, or may have up to 7 components, or maybe more if it's a complicated class. So has a will be more often applicable than is a, because you inherit from one place or maybe 2 places, but you have elements which are many more. So both the relation types is some kind of containment, because even with derived classes, you are having the base class, you are containing, so to say, the functionality of the base class. So there is some kind of containment in both of them. In some way, has a relation can provide the functionality of is a relation. So sometimes you are working with a language like system Verilog, where multiple inheritance is not possible, and you want to kind of have multiple inheritance. So you will be doing it by way of inheriting from one class, and instead of inheriting from the other class, uh, you will have the other class present as a component of the, so you will kind of inherit by way of creating a component, or the object of the base class as a component. Okay, so this will see how this gets done in when we implement TLM ports. So there are some places where inheritance would have been more proper, but since so in system C that happens via inheritance. In system Verilog, since only single inheritance is possible, it is done via composition. Since okay, so we already covered it. Now we come to the next one. That's the second last principle, which is dependency inversion principle. But just as a background, you have layering. So there is component A, which is higher abstraction. Then you have component B, which is lower abstraction. and there is component C, which is still lower abstraction. So in non-objective oriented kind of programming, B will be dependent on C and A will be dependent on B. And since the lower layers tend to have many more components, so there will be B will be dependent on many components. Okay, so that thereby there'll be tight binding, and similarly A will be dependent on many B layer components, because the lower layers tend to have more components, because those are the details. Lower layers are the details. As we go high, abstraction reduces and details are less, so there'll be less number of components. As the software is developed using layered approach, the upper layers often need to call the functions and methods made available by the lower layers. So there's obviously binding, wherein the upper layers are calling functions of the lower layer. An example, for example, a utility layer library for a modem related application would provide parity and CRC function. A higher level protocol layer would need this to call these functions to check whether parity or CRC of the data received in the ingress channel is maintained or not. So parity holds, or what is the CRC. So we already saw the Ethernet frame class that we had developed earlier in the earlier slides. So CRC was a service provided to the higher layer. So CRC will be called by the higher layer, and therefore there is dependency. And this is exactly what we want to avoid. And this is exactly related to when we, a few moments back, I showed you this modem example where we had transport layer and session layer. So in that example, the lower layer methods, if you are calling them directly, then that is increasing binding. If we call them through interfaces, then the binding gets reduced. Okay, so that's what dependency inversion layer, dependency inversion principle is about. So what you do is, instead of calling service methods from C directly, there'll be an abstract class, and that will define what kind of services you need from C. And then the components in the C layer will inherit from that class. And those components will define those services, while the B level components will use those services through that interface. Okay, so now in a way, we are inverting the binding. So instead of B getting B getting dependent on C, C is dependent on B. Fine. So C will need to implement the services which are required by B, rather than B having to call services which are provided by C. Is the other way around. C is told, okay, this is what I require, and now go and implement it. Okay, so this is done via inheritance, and then we are reversing the dependency. And actually we are not even reversing, because what happens is in this abstract class does nothing. It just defines the services and doesn't implement, just defines what all services will be there. So this particular class will be just a plain contract, and contract will not change. Okay, so in case there are many, for example, this was a modem class. So in case there are many modems, all of them need to adhere to this interface, and therefore it's not a binding at all, because this interface is not going to change. Binding will be there only if there is something which is changing. So then there is binding. If it's not going to change, then even if you call it a binding, but this binding amounts to nothing, because it's not going to change. That relation is not going to change. That contract is not changing. So the dependency inversion principle suggests high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Okay, now this is the this is the most important principle which needs to be understood in case you need to understand how UVM works. The top layer, which is the UVM layer, just tells you that if you are creating a component, then what all details of the component is required. Okay, the highest layer will implement the high level algorithms, how to run the simulation, how to run the whole test bench. So that is defined in the, and how, how, when to terminate the test bench, all that functionality is, so those are the higher level functionality which are generic enough, which can apply to any test bench. So those are the generic algorithms, top level simulation or test bench algorithms. They are already defined for you. So that's why methodology is top level. And then you need to fill in the lower level details. You need to tell, okay, I'm defining the driver. So what's particular about this driver? How is it? Because it's not a generic driver. Generic driver is the base class, and this is specific for example, for AVST. So it will need the AVST details to be filled in. So first you will tell this is a driver, and this driver is specific to AVST so driver, the generic driver is having it's generic in that sense also, that it's a parameterized class. The class parameter needs to take what's the kind of sequence item it takes, and then so you will be defining that it's a AVST driver, and you'll associate it with AVST sequence item, and then you will have the details of the AVST BFM because it's a driver. Okay, so you are filling in the lower level details, and UVM is providing you the top level algorithm. So last principle, the interface segregation principle. Many client-specific interfaces are better than one general purpose interface. If you have a class that has several clients, rather than loading the class with all the methods of the client's need, create specific interfaces for each client and each client and multiply inherit them. So there is some typo over here. For each client and multiply inherit them into the class. So this is specific to multiple inheritance. System Verilog does implement multiple inheritance in Java way. So there is something called class inheritance in System Verilog, but it is not used in UVM because at least 5 years back, I was told one of the big EDA vendors doesn't implement class interfaces. So that's why UVM never got a chance to have class interfaces. But this principle applies to class interfaces or multiple inheritance. So we will kind of skip this principle, but we'll read it once. If clients share interfaces, a change in interface of one client would spoil everything. In a way, you can apply this principle to the hardware interfaces, to the module interfaces that you have in System Verilog. So for example, if you have AVST bus as well as AXI bus as well as USB, so the principle says just don't have one single interface which mixes up everything. Have a separate one for AVST, have a separate one for AXI, and a separate one for USB, because there'll be the USB clients will just need the USB kind of wired signals, and AXI clients will just need the AXI wired signals. In case you create a big interface with everything, if instead of AXI you want to have AHP, so then all the clients will get affected. The connections that you make everywhere will get affected. Similarly, you can think in terms of software. If there are clients who want to look at, say, a driver, so in UVM, for example, if the driver has to interface um, with the sequencer, then it does through, because today we don't have multiple interfaces available in System Verilog, so we do it through TLM ports. So as I said, we utilize components to implement multiple interface kind of systems, and where you don't have multiple interface construct available like in system Verilog. So instead of that, we'll create multiple ports and exports and have that interface available through the ports and export. So slightly complicated concept. It's okay if you don't understand it right away, but it will be good if you understand it in that sense. So if a client share interfaces, a change in interface of one client would spoil everything. So let me end this session and these slides, this part of the session by giving you an example for this particular principle. So we have a train bogie. Now, train bogie is a vehicle because it moves. It is also a hotel kind of thing because every night people will be sleeping in that train bogie. So the bed sheets and uh, everything needs to be cleaned up every morning, and bed sheets need to go to laundry. So that kind of service, hotel kind of service, also needs to be provided. Then a train bogie has electric connection. So there is an interface for the electric department also, right? Who will maintain the electric gadgets or equipments in that train bogie. And the same train bogie has a reservation system because the tickets need to be reserved. Now, the segregation principle says that when you are making train bogie, instead of having a common class contract wherein you define all these functionalities in a single class and make them public, you instead derive this train bogie from different interfaces. So the train bogie is implementing different interfaces. So one interface is for the electrician, another one is for the people who maintain cleanliness, another one who provide food, for example, lunch, dinner, etc. Yet another one for the reservation system. Okay, so in case you just mix up and create one class with all these functions defined, then clients will have difficulty in, so one function gets changed and it will start affecting other people also. So thereby, in System Verilog allows that, though it's not used by UVM, a good implementation would be the train bogie will implement various interfaces, and those interfaces will be used by the clients to look at the train bogie. For an electrician, that train bogie will have a different view because he'll only see the electrician interface, and for the vendor who supplies food, it will have a different view. Okay, so all those views are kept different, and since those views are interfaces, they are contracts. So the contracts shouldn't change. That's one of the first assumptions we made. So the point is, if we just have one single contract, that means one single interface, there can be a change in contract because we are digitizing the train bogie, and therefore electric equipments need to change, but that doesn't necessarily mean that the food service has to change. So thereby, to minimize bindings, we need to have multiple interfaces. So that ends up this session, and now we will quickly, we still have 15 minutes left, almost, not 15, 10 minutes left. So we'll quickly take a look at the test bench of the more complicated SHA3 example that uh, we were having as a test bench, and we try to understand how it is different and what are the various components. So we'll do it quickly. I'm sorry that things are getting delayed, and probably I'm not even able to do justice to the slides as well, to the level I should have, but the recordings will be available. The forum is available. If you don't understand some part, then do let me know If you want me to repeat some part tomorrow, do let me know. If there are many people asking me to repeat, I'll repeat that part. Okay. So now we go to, before I go anywhere, I just take out the changes that I did here for explaining various stuff. So we go to AVMM. And inside AVMM, we go to the test bench. Before that, we also quickly cover the test bench, the native test bench. So the native test bench had only 3 test cases. One was small, one was medium, and one was large transaction. All three were all the three were um, directed test cases. And as you can see in this test bench, there is empty message and what should be the output of empty message and so on. Now this DUT is complicated because it has various modes. So there is one mode where SHA3 224 needs to be implemented. There is another mode where 256 SHA3 256 that needs to be implemented. There is one mode where 384 that needs to be implemented, and there is one mode where 512 needs to be implemented. Okay, now these are the 4 modes in which SHA3 can operate. You know, even SHA2 had different modes. So SHA2 is the encryption which gets invoked when you do SSH from one machine to another. So SSH is a secure connection, or even when you are visiting a website and instead of doing HTTP, you have HTTPS. So that S stands for SSL connection, which today currently it's implemented using SHA2 encryption algorithms. So now the test bench that we are having, it's specific to SHA3. So it's kind of something which is practically not in much use today, but it's a standard which is getting implemented across the world. Now, SHA3 can have various security levels. So 224 is lower one and 512 is the highest one. Okay, so whenever there is a test case in the directed test case, so for empty message, he has 3 outputs which are coming out. So the security mode is also about like what's the length of the output you are getting. And then for short message, again, what's the expected output? So he's storing that. All these control M's which are coming, please ignore that. This is like the file is written in Windows and it's I'm reading it in Linux. So there is some extra characters at the end of the line which need to be ignored. Okay, and then for the long message, so the output will be more specific even if the message is long. So the output is 224, 256, 384 or 512 bits long. Okay, and what are those messages? Those are not short message. So here, so short message is only A, B, C. Okay, and this is the, so it's given in the comment. So this is the string generated out of ABC. ASCII string ABC has this representation in hex. Okay, and for the long message, he is using, where is it defined? So it's not given right here, but it will be there somewhere later. So for short message, okay, so I just search for ABC. Huh, what's wrong? Okay. Okay, so this is the short message output, and then there'll be test cases, and this is where he's connecting the DUT, and so you can you can see right away that as I was saying, for very simple DUTs, there is a lot of boilerplate in UVM, For more complicated ones, that boilerplate will become insignificant. So this is a native test bench written in plain Verilog, and you can see it is 600 lines long, and it's just doing 3 test cases. While we will see in embedded UVM, this test bench will be similarly long, but it will be doing constraint random simulation, which is much more thorough. Okay, so this you can see is the BFM, and as you can see, everything, because it's done natively without any layering, so the functionality and everything, it's all mixed up. So he is calculating which particular byte to drive somewhere. So he's calculating, he's making that out in the BFM only, while it should have been made out in the sequencer. So that's a different layer. One thing is about reusability. So this SHA3 is having an interface for communication with the rest of the world. So that interface may be AXI or some standard interface. So the reusability part says that if you have a driver for, say, for AXI, you should be able to use that AXI driver for another module which also needs AXI. So obviously it's not happening here, because he is finding out what data to drive as part of the BFM, so that you know you are not segregating the functionality of the BFM uh, from the functionality of the module. So reusability is one sacrifice that you are making here. Okay, so let's not get too much bothered about what he is doing here, because it's very complicated. I just wanted you people to see how complicated it is. We will instead take a look first at the slides to make out what the interface is about. Okay, and then we are running late, so I'll just stop at the slides, and tomorrow morning we'll look at the test bench and see how those things are implemented. Okay, so let me just pull up the slides first. So those are the slides where this. So those are the ones I used yesterday. So these slides. In the end, so I couldn't cover it yesterday, so I'll just cover it now. Okay, so I'll also make sure that these slides are available to you, so that you can take a look, because I have very limited time to explain all this. So in the end of the slides, you have how this particular module takes input. So it's not only about the AVMM bus, it's also about that there are registers which need to be written. So actually, in this particular module, there are no registers which need to be written. There are registers which can be read. So there is a version register which defines the version of the hardware design. There is a control register, and there is a status register. So what needs to be done is, we define it here. Upper 30 bits of control are don't care, so we don't have any use of 30 bits of control, while the first bit and the second bit, those are the least significant bits. On the first bit, we signal init, so we say that, okay, we are giving the first frame, first not frame, first, in the sense that first set of data, and then there will be a set of data. So okay, let me first explain what the frame means. Since the input can be, so the interface actually is AVMM based, but AVMM means you are reading and writing into registers. And when you are reading and writing into registers, there'll be a limit on number of registers, because you are storing stuff in memory, and memory will have some size. So what happens in this case is, we have registers for reading and writing, Okay, and those registers should be somewhere here. Yeah. So we have this space from 200 to 300. That means 256 registers in which we can write. Okay, but we actually have only 200. The 56 part is not implemented in the design. I mean, it's not part of the memory. So it's in the address space. So that part is not implemented. That address space is not implemented. So from 200 till something like because you have 200 bytes available, so it will become something like uh, 128 128 in hex. So that many addresses are available where you write a frame first, and then so there are 200 registers to write. So depending on what mode you want to use that particular SHA algorithm, you will leave some bytes empty. Okay, so that all that algorithm is explained here. I just don't want to overshoot too much because it's already 32, so that's why I'm doing it very fast. So let's do one thing. Let's break here. I'll explain all this tomorrow only. So I'll explain this algorithm and then we'll go over SHA3 and we'll see how this complicated stuff is implemented via virtual sequencer and the test bench. Okay, before that, we have a quiz today. So we have 10 minutes of break, and after that at 2:45 the quiz starts. Please start it in time. Like last time, what happened was people started late. Some people started late, and then they couldn't submit in time. So please start it on time so that we can have all the submissions. There are prizes to be won. Intel is sponsoring 5 DE10 light boards, and the top 5 people accumulatively. So all the 5 quizzes accumulated, the top 5 people will be getting 1 board each. So more than the board itself, it is also a recognition from a big company like Intel that you have achieved a good score in the quiz. So it carries a lot of weight, much more weight than the certificate itself. So do best of luck for the quiz and do attempt it very seriously. Okay, so this portion I'll cover tomorrow because I don't want to overlap with the quiz, and I'll go through the test bench also tomorrow.
Thank you, sir. So all the participants, please note that right now the time is 2:33. We will start at 2:45. All the details are already uploaded in the drive. I request you all to please check. The link is also provided. We are getting a lot of query regarding the same. You please check the drive. There is a drive which is being shared with you. The link is provided. The timings are given to you. There will be 20 questions and we will be giving you 30 minutes. So 10 minutes extra grace time is given to all of you to deal with the issue. I request you all to please make sure that you are submitting it before time. So right now, if we see the time is 2:34, we will close this event right now because if you are connected here, you will not be able to concentrate there. So we will close the link right now. I request Poddar, if there is any other instruction that you need to give, you just please address the participant.
No, ma'am, you have already covered all the points. I'd just like to mention the participants, please visit the link, drive link that has been provided with you. Here you will find a folder as quiz. Please enter into that folder. There you will find a doc file of link for MCQ. There you can find the link for the second MCQ. Please follow that. Thank you.
Yeah. May I request you to please drop the no, okay, fine. So already we have shared it. So I request you right now, the time is 2:35. You are left with 10 minutes. Please make your system ready for the same and connect us for the quiz at 2:45. Make sure that you are submitting everything before 3:15. Don't wait for 3:15. Please submit it before 3:15. We are already giving you 10 minutes of grace time for all the issues that you faced last year. So all the best. Thank you, Puneet sir. With this, sir, we are closing the event so that the participant will pay more attention there.
Okay,
Thank you,
thanks.
Puneet.
Okay,
Thank
talk
you.
to you later. Bye.